The mirror has been open to the dark for hours. Starlight has fallen onto gold-coated segments, crossed cold optics, and landed on detectors kept colder than any winter on Earth. At first, the frame looks almost empty, a black field interrupted by a few bright points and a faint spray of noise. Then, the exposure deepens. The scattered points become galaxies. Some are blue and close by cosmic standards. Some are flattened into small disks. Some are red, stretched and blurred by the long journey their light has taken before it reached the telescope. In one corner of the image, a smudge that would fit under the point of a needle has been traveling toward us since before the sun existed in its present form. A frame like this does not show the whole universe. It does not even show a large piece of the sky. It shows a patch so small that you could cover it with a grain of sand held at arm's length. Yet inside that small patch are thousands of galaxies, and inside many of those galaxies are billions of stars. Around some of those stars there are planets, moons, rings, asteroids, dust belts, frozen fragments, failed worlds, and maybe worlds with oceans sealed beneath ice. The image is not a painting of infinity. It is data gathered by a machine, corrected for noise, aligned by software, and translated into colors human eyes can understand. The question hidden inside that image is simple to ask and almost impossible to feel in full. How big is the universe really? Not the night sky above your city, not the solar system, or the Milky Way, or the clusters of galaxies that fill the deep maps of astronomy. The question reaches toward the entire cosmos, toward the part we can observe and the part we may never observe, toward the difference between what light has had time to bring us and what may exist forever beyond our horizon. It is a question about distance, but also about time, expansion, measurement, and the limits placed on knowledge by the speed of light itself. The answer begins with a correction. When people hear that the universe is about 13.8 billion years old, it is natural to imagine a sphere about 13.8 billion light-years in radius. Light has had 13.8 billion years to travel, so the farthest visible things should be 13.8 billion light-years away. That sounds reasonable. It is also wrong, not because light has broken its own speed limit, and not because galaxies have flown through space faster than light in any ordinary local sense. It is wrong because the space between us and those galaxies has been expanding during the entire journey. Today, the observable universe is roughly 92 to 93 billion light-years across. The number varies slightly with the cosmological parameters used and the way the distance is rounded, but the scale is the same. In every direction, the edge of what we can observe lies at a present-day distance of about 46 billion light-years. That edge is not a wall. It is not a shell of matter. It is not the place where the universe ends. It is the limit of the region from which light has had time to reach us since the universe became transparent and since the cosmic expansion allowed signals to cross the distance between there and here. If these careful journeys through the cosmos are why you return, subscribing keeps the next one close. The numbers sound impossible only because ordinary distance teaches the wrong instinct. On Earth, a kilometer stays a kilometer. A road between two cities does not stretch while a car is driving along it. Space on cosmic scales behaves differently. Light from a distant galaxy may spend more than 13 billion years crossing the universe, while the distance between that galaxy's present location and ours grows far larger than the travel time alone would suggest. The light is old. The source, if it still exists as a recognizable galaxy, is now much farther away than it was when those photons began their journey. Astronomers separate these ideas with careful language. Look-back time tells how long the light has been traveling. Proper distance, comoving distance, luminosity distance, angular diameter distance, and redshift describe related but different ways of measuring separation in an expanding universe. These distinctions can feel like technical clutter, but they matter. They are the reason a galaxy whose light has traveled for over 13 billion years can have a present-day distance of more than 30 billion light-years. They are also the reason the observable universe can be far larger than the simple age of the universe multiplied by the speed of light. To understand that scale, it helps to begin close to home, where distance is still almost manageable. The Moon is about 384,000 kilometers away on average. Light crosses that gap in a little more than 1 second. When you look at the Moon, you see it as it was just over a second ago. The delay is real, but your life is too slow to notice it. A radio command sent to a spacecraft near the Moon can be answered quickly. The system feels connected, close enough that human beings have walked there, returned samples, left instruments, and watched Earth rise above a gray horizon. The Sun is much farther away. Light takes about 8 minutes to cross the distance from the solar surface to Earth. The sunlight on your hand is not present in the strictest sense. It is a message from 8 minutes ago, produced by plasma moving under magnetic fields, crossing space as electromagnetic radiation, and arriving at a planet that depends on it. If the Sun disappeared, which it will not do in that way, Earth would continue along its orbit and continue receiving daylight for those minutes before the change reached us. Even in the inner solar system, observation is already a kind of delayed knowledge. Mars can be 3 light minutes away at favorable oppositions, or more than 20 light minutes away when it lies on the far side of the Sun. That delay shaped every rover landing, every orbiter correction, every weak signal returned from the red planet. Engineers cannot drive a rover on Mars the way a person drives a vehicle on Earth. They send instructions, wait, receive images, reconstruct the terrain, and plan the next movement. The planet is close enough to study in detail, but far enough that control becomes conversation with the past. Jupiter is farther still, a world of cloud belts, lightning, radiation, moons, and magnetism so large that it creates its own violent environment. Light from Jupiter takes roughly half an hour to 3/4 of an hour to reach Earth, depending on the positions of the planets. The Galileo spacecraft, and later Juno, did not reveal Jupiter by magic. They measured charged particles, radio emissions, gravity, magnetic fields, infrared heat, water vapor, and the pull of the planet on their own trajectories. Each result arrived after a delay, and each delay reminded mission teams that the solar system is not a diagram on a page, but a set of physical distances. Saturn sits far enough away that sunlight is already faint compared with the light received at Earth. Its rings, bright in telescope images, are made of countless icy particles ranging from grains to boulders, orbiting within the planet's gravity. The Cassini spacecraft took images of ring shadows, moon flybys, geysers on Enceladus, hydrocarbon lakes on Titan, and storms turning through Saturn's atmosphere. The radio signal from Cassini was never immediate. By the time a tone reached a dish on Earth, the event that produced it had already happened. Space exploration teaches distance through waiting. Beyond Neptune, sunlight becomes weak enough that noon on a distant icy body would look like a kind of deep twilight. Pluto, Arrokoth, scattered disk objects, and the imagined reservoir of comets in the Oort cloud belong to an outer domain where orbits can take hundreds, thousands, or millions of years. The Oort cloud, if models are correct, may extend a large fraction of a light year from the Sun. Even this enormous shell of icy bodies is still not the edge of the universe. It is only the loose outer boundary of one star's gravitational influence, one small system inside one galaxy. The nearest star system, Alpha Centauri, is about 4.3 light-years away. A beam of light that leaves Earth today would need more than 4 years to arrive there. A spacecraft moving at the speed of the fastest probes humanity has built would need tens of thousands of years. The distance is so large that it breaks the scale of ordinary exploration. Yet in the galaxy, it is close. It is a neighboring system. It sits in the same small region of the Milky Way, part of the same general stream of stars orbiting the galactic center. A light year is a unit invented because kilometers and miles become unmanageable too quickly. 1 light-year is about 9.46 trillion kilometers. That number is not an exaggeration. It is the distance light travels in a vacuum in 1 year, moving at about 300,000 kilometers per second. A single light-year already exceeds the scale of human movement. 4 light-years to the nearest neighboring stars. Hundreds of light-years to bright clusters and nebulae. Thousands to the center of familiar constellations as physical arrangements. Tens of thousands to cross the galaxy, millions to reach neighboring galaxies, billions to reach the edge of the visible cosmic past. The Milky Way is about 100,000 light-years across, perhaps somewhat larger if its faint outer disk and stellar halo are included. The Sun sits far from the center, about 26,000 light-years out, moving with the local disk around the galaxy once every few hundred million years. During one orbit of the Sun around the Milky Way, entire families of species can arise and vanish on Earth. Mountains can rise, erode, and disappear. Oceans can open. Climate can shift. The galaxy is not only wide in space, it is slow in a way that human history cannot easily hold. From inside the Milky Way, we see the galaxy as a band of light across the sky, dense with stars and dust. Optical telescopes cannot see cleanly through the whole disk because interstellar dust absorbs and scatters visible light. Infrared observations reveal more. Radio telescopes trace hydrogen gas through the 21-centimeter line. Surveys of stellar positions and motions map the disk, the bulge, the spiral arms, and the streams of stars left behind by smaller galaxies pulled apart by gravity. The galaxy is not a flat symbol. It is a dynamic system of stars, gas, dust, dark matter, and a central black hole. At the center of the Milky Way sits Sagittarius A star, a black hole with about 4 million times the mass of the Sun. Its presence is known not because it looks like a dark hole in ordinary images, but because stars whip around an unseen mass in tight orbits. Infrared telescopes watched those stars for decades, measured their positions, traced their paths, and revealed the gravitational source they orbit. Later, radio telescopes working together across Earth reconstructed a shadow-like image of the region near the event horizon. Even the center of our own galaxy is known through patient measurement, not direct touch. If the solar system were shrunk until Neptune's orbit fit inside a small room, the Milky Way would still stretch across a continent. Most of it would be empty by human standards, but not empty in the physical sense. There would be gas clouds where stars form, supernova remnants glowing in X-rays, cold molecular regions dark against background stars, white dwarfs cooling over billions of years, neutron stars rotating with radio beams, black holes feeding quietly or not at all, and planets moving around stars too faint to see with the unaided eye. Scale in astronomy is not just about size. It is about the number of things that fit inside the size. Star clusters give a smaller but still enormous measure of galactic structure. The Pleiades are a few hundred light-years away, young by stellar standards, their blue stars moving together through space. Globular clusters are older, denser, and often far from the disk, containing hundreds of thousands of ancient stars packed into spherical swarms. A globular cluster can be over 10 billion years old, meaning many of its stars formed when the universe was much younger and the Milky Way was still building itself through mergers and gas flows. Every cluster is a record of conditions that no longer exist. Nebulae look soft in images, but they are made of matter. The Orion Nebula is a stellar nursery about 1,300 light-years away, where ultraviolet radiation from young stars lights surrounding gas. Pillars and filaments in such regions are shaped by radiation, winds, gravity, turbulence, and magnetic fields. In visible light, they can look like painted clouds. In infrared, embedded stars appear through dust. In radio maps, cold molecules reveal the reservoir from which future stars may form. The same physical universe that contains galaxies also contains dense knots of gas where planetary systems begin. Supernova remnants measure another kind of distance. The Crab Nebula is the expanding debris of a stellar explosion observed on Earth in 1054. The light crossed thousands of years before reaching human witnesses, and the material continues to expand into space. X-ray images show energetic particles and magnetic structures near the pulsar at its center. Optical images show filaments of gas rich in elements forged inside the dead star. The remnant is not only beautiful, it is evidence that heavy elements are made and distributed through stellar death, later becoming part of planets, atmospheres, oceans, and living chemistry. The Milky Way itself contains perhaps hundreds of billions of stars, though the exact number depends on how many faint red dwarfs and low-mass objects are counted. Around many of those stars are planets. Transit surveys have watched stars dim slightly as planets pass in front of them. Radial velocity measurements have detected stars wobbling under the gravity of orbiting worlds. Direct imaging has captured a few young giant planets far from their stars. Spectra have begun to reveal atmospheres in some systems. The galaxy is not a collection of lights only. It is a planetary environment on a scale too large for any probe to cross in human time. Still, the Milky Way is only one galaxy. The Andromeda Galaxy is about 2.5 million light-years away, close enough to appear as a faint smudge in a dark sky, and far enough that its light began traveling before modern humans existed. Andromeda contains hundreds of billions of stars, a central bulge, dust lanes, satellite galaxies, star-forming regions, and a dark matter halo. It is moving toward the Milky Way, and in several billion years the two galaxies will begin a long merger. The collision will not be like two solid objects striking. Most stars will miss one another because the spaces between them are vast. Gravity, gas, and dark matter will do most of the work. The local group includes the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller galaxies. Some are dwarf spheroidals with little gas and old stars. Some are irregular galaxies, still forming stars. Some have been stretched into streams by tidal forces. Their positions and motions reveal a small gravitational community, roughly 10 million light-years across. On the scale of the observable universe, the local group is nearly nothing. On any human scale, it is unreachable territory, containing more stars than all the grains of sand on Earth by enormous margins. Moving outward, galaxies gather into groups and clusters. The Virgo cluster lies tens of millions of light-years away and contains thousands of galaxies bound by gravity. Its galaxies move through a deep gravitational potential filled with hot gas visible in X-rays and a larger amount of dark matter inferred from motions, lensing, and mass measurements. Galaxy clusters are among the largest bound structures in the universe. They are not static. Galaxies fall in. Gas is stripped. Black holes feed. Star formation changes. Clusters grow by merging with other clusters over cosmic time. Between clusters, galaxy surveys reveal filaments, sheets, and voids. This is the cosmic web, the large-scale pattern formed as gravity amplified small density differences from the early universe. Galaxies are not sprinkled randomly through space. They trace a structure shaped by dark matter, ordinary matter, expansion, and time. Long filaments can stretch for hundreds of millions of light-years. Voids can span enormous volumes where galaxies are sparse. These voids are not absolute nothingness. They contain dark matter, thin gas, radiation, and occasional galaxies. Their emptiness is relative, but on cosmic maps, the contrast is profound. The Sloan Digital Sky Survey and other redshift surveys turned galaxy positions into maps with depth. A galaxy's redshift shows how much its light has been stretched by the expansion of space, and with a cosmological model, it becomes a distance indicator. Millions of points build a three-dimensional pattern. The result resembles foam, with galaxies collected along walls and filaments surrounding vast cavities. It is one of the most important images in modern cosmology because it shows that the universe has structure on large scales, but also that beyond a certain scale the structure averages out. That averaging matters. On scales of individual stars, matter is clumped. On the scale of galaxies, it is clumped more. On the scale of clusters and filaments, the clumping remains obvious. But on scales of hundreds of millions of light-years, the universe appears roughly homogeneous and isotropic, meaning similar in every direction and at every location when viewed broadly enough. This principle does not say every place is the same. It says the largest pattern does not seem to have a preferred center or direction. Without that assumption, the equations used to interpret cosmic expansion would become far more difficult and far less constrained. The observable universe is centered on us only in the observational sense. Earth is not at the physical center of the cosmos. Every observer in every galaxy has their own observable universe, defined by the region from which light has had time to reach them. An astronomer in a distant galaxy would see a different horizon. Some of the galaxies we see would lie outside their view. Some galaxies beyond our view might lie inside theirs. The horizon is not a special place in space. It is a consequence of age, expansion, and the finite speed of signals. The most distant ordinary light we can detect from every direction is the cosmic microwave background. It is not starlight. It is the cooled remnant radiation from the early universe, released when the cosmos became transparent about 380,000 years after the Big Bang. Before that time, free electrons scattered photons so often that light could not travel far. The early universe was opaque, not because it was empty, but because it was dense, hot, and filled with charged particles. When electrons combined with nuclei to form neutral atoms, photons began to move freely through space. Those photons have been traveling ever since. Expansions stretched their wavelengths from visible or infrared light into microwaves. Today they form a nearly uniform background at about 2.7 Kelvin, just above absolute zero. Radio and microwave instruments can detect this glow across the entire sky. It looks almost perfectly smooth until the measurements are sensitive enough to reveal tiny temperature differences, variations of only about 1 part in 100,000. Those differences are the seeds of later structure. They mark regions that were slightly denser or slightly less dense when the universe was young. The cosmic microwave background is often described as the baby picture of the universe, but the phrase can be misleading if it makes the image seem simple. It is not a photograph taken from outside. It is radiation arriving from every direction, from the surface of last scattering, a spherical horizon around us because we receive the old light from all around. The pattern encodes density, motion, curvature, ordinary matter, dark matter, and the conditions under which later galaxies formed. Missions such as COBE, WMAP, and Planck did not merely take pretty pictures. They measured the early universe with precision. Planck mapped the cosmic microwave background at multiple frequencies, separating foreground emission from the Milky Way and other sources in order to isolate the ancient radiation. The map is filled with small fluctuations, but each fluctuation is part of a statistical pattern. Cosmologists compare that pattern with models. Peaks in the angular power spectrum show the imprint of sound waves in the hot early plasma. The spacing and height of those peaks help determine the age, composition, geometry, and expansion history of the universe. A sky map becomes a measurement of cosmic parameters. The result is the standard cosmological picture often called lambda cold dark matter, or lambda CDM. It is not the final answer to everything. It is a model that fits a remarkable range of observations: the cosmic microwave background, the large-scale distribution of galaxies, the abundance of light elements, the growth of structure, and the accelerated expansion measured by distant supernovae. In this model, ordinary matter makes up only a small fraction of the cosmic inventory. Dark matter provides much of the gravitating mass that helps structure form. Dark energy, represented in the simplest version by a cosmological constant, dominates the present expansion. Ordinary matter is what makes stars, planets, gas clouds, dust grains, people, telescopes, and the detectors that measure the sky. It is made of atoms and known particles. Yet by mass energy accounting, it is only about 5% of the universe. Dark matter makes up roughly 27%. It does not emit, absorb, or reflect light in any way we have detected, but its gravity is visible in galaxy rotation curves, galaxy cluster motions, gravitational lensing, and the cosmic web. Dark energy makes up roughly 68% and is the name given to whatever is causing cosmic expansion to accelerate. These percentages can sound like certainty, but they are not the same kind of knowledge as holding a rock in your hand. Dark matter is inferred through gravity. Dark energy is inferred through the expansion history of the universe. The measurements are strong, but the underlying physical nature remains unresolved. Scientists do not know whether dark matter is one particle, several kinds of particles, primordial black holes in some limited fraction, or something more subtle. They do not know whether dark energy is a true cosmological constant, a dynamic field, or a sign that gravity behaves differently on the largest scales. The names mark evidence and ignorance together. The size of the observable universe depends on this expansion history. If the universe had expanded differently, the distance to the cosmic microwave background would be different. If the balance of matter and dark energy changed, the horizon would change. Cosmology is not a tape measure stretched across empty space. It is a reconstruction of how distances evolved while light traveled. The number 46 billion light-years to the edge of the observable universe is not simply observed by looking and reading a label. It is calculated from redshifts, expansion, matter density, dark energy, curvature, and the age of the cosmos. Redshift is one of the central clues. When space expands, wavelengths of light traveling through it stretch. A galaxy's spectral lines shift toward longer, redder wavelengths, and the amount of shifting tells astronomers how much the universe has expanded since the light was emitted. Spectrographs turn faint galaxy light into measurements. A line from hydrogen, oxygen, carbon, or another element appears displaced from its laboratory wavelength. That displacement becomes a redshift. Redshift becomes history. The more the light has been stretched, the more the universe has expanded during its journey. At small distances, redshift is complicated by local motions. Galaxies can move toward or away from one another under gravity, and those motions add to or subtract from cosmic expansion. In nearby clusters, a galaxy's peculiar velocity can matter as much as the Hubble flow. At great distances, expansion dominates. Edwin Hubble and others found the pattern in the 1920s. More distant galaxies generally have larger redshifts. The universe is expanding. The relationship has been refined for a century, but its basic meaning remains one of the major turning points in human understanding of the cosmos. Distance measurements build upward like scaffolding. Radar can measure distances inside the solar system. Parallax measures nearby stars by the tiny shift in their positions as Earth moves around the Sun. Cepheid variable stars, whose brightness relates to their pulsation period, extend the ladder to nearby galaxies. Type 1a supernovae, bright stellar explosions with calibratable luminosities, reach much farther. Redshift surveys extend beyond that, but redshift must be interpreted through a cosmological model. Every rung has uncertainty. Every rung is tested against the others. The observable universe is measured through this chain, not through a single act of seeing. Standard candles and standard rulers are different tools for the same problem. A standard candle has a known brightness, so its apparent dimness reveals distance. A standard ruler has a known physical size, so its apparent size reveals distance. Baryon acoustic oscillations, the fossil scale of sound waves in the early universe, provide one cosmic ruler. The cosmic microwave background provides another reference. When these tools agree, confidence grows. When they disagree, as in some measurements related to the Hubble constant, the disagreement becomes important because it may point to hidden errors, unrecognized astrophysics, or physics beyond the simplest model. The Hubble constant tension is a reminder that cosmology is not finished. Measurements based on the early universe, especially the cosmic microwave background interpreted through lambda CDM, give one value for today's expansion rate. Some measurements based on nearby distance ladders and supernovae give a higher value. The difference is not large in everyday terms, but it is persistent enough that scientists take it seriously. It does not mean the universe is unknowable. It means the most precise map of cosmic size may still contain a mismatch at the level where better instruments and better analysis can matter. Even with unresolved tensions, the broad scale is secure. The observable universe is tens of billions of light years in radius, not because we see objects traveling faster than light through local space, but because the metric of space itself has changed over time. General relativity allows space to expand. Distant galaxies can recede from us at effective rates greater than the speed of light due to expansion without violating the local speed limit, because no object is outracing a light beam through its immediate neighborhood. This is subtle, and it is why simple analogies often fail. The raisin bread analogy is useful, but incomplete. As dough rises, raisins move apart because the dough between them expands. No raisin is the center. Every raisin sees other raisins receding. On the surface of an inflating balloon, dots move apart as the surface stretches. No dot is the center of the surface. These analogies help, but they also mislead because bread and balloons expand into surrounding space, while the universe is not known to expand into anything external. The expansion is a change in distances within space itself. The Big Bang was not an explosion into pre-existing darkness. It was an early hot dense state of the universe followed by expansion and cooling. Every region of space we observe today was once much hotter and denser. The galaxies are not flying away from a central blast point. Distances between unbound galaxies increase as space expands. Bound systems, such as atoms, planets, star systems, galaxies, and even galaxy clusters, do not expand with the universe in the same way because local forces and gravity hold them together. Cosmic expansion matters most across the largest scales. If you run the expansion backward in the equations, the observable universe becomes hotter, denser, and more uniform. Galaxies disappear into gas. Atoms lose electrons. Nuclei break into protons and neutrons. Earlier still, the conditions become more extreme, and the physics becomes less directly tested. The Big Bang model describes the evolution from an early hot dense state, not necessarily an absolute beginning from nothing. Scientists can speak with confidence about some early epochs and with more caution about the very first fraction of a second. The evidence is strong, but it does not remove every question. Cosmic inflation is one proposed early episode, a rapid expansion that may explain why the universe appears so flat and uniform on large scales, and why tiny quantum fluctuations could become the seeds of cosmic structure. Inflation is widely studied and fits many observations, but the exact mechanism remains uncertain. The energy field that would have driven it has not been identified. Some versions predict signatures that have not yet been detected. When the script of the universe is read from the cosmic microwave background, inflation appears as a powerful possible chapter, but not one with every sentence confirmed. The observable universe begins after inflation in the practical sense, because that is where our evidence becomes richer. Nucleosynthesis in the first minutes produced hydrogen, helium, and small amounts of lithium. The predicted proportions match observations well enough to form one of the pillars of Big Bang cosmology. Hundreds of thousands of years later, the cosmic microwave background was released. Hundreds of millions of years after that, the first stars and galaxies began to form. Each stage is supported by different evidence: light element abundances, background radiation, galaxy surveys, simulations, and the spectra of extremely distant objects. Looking far away means looking back in time, but not in a simple straight hallway. A galaxy, whose light was emitted when the universe was only a few 100 million years old, may now be far beyond the distance suggested by that look-back time. In deep infrared images, some of these early galaxies appear as red points or faint smudges. They are studied through photometric colors, spectroscopic redshifts, gravitational lensing, and comparison with models of early star formation. Each one helps fill a piece of the story, but none of them is the edge of everything. The James Webb Space Telescope extended the study of early galaxies because infrared light is essential for seeing highly redshifted objects. Light that began as ultraviolet or visible radiation from young stars is stretched into the infrared by the time it reaches us. Webb's mirrors and instruments were built to collect and analyze that light. A galaxy in a Webb deep field can be faint enough that its signal barely rises above noise, but with enough exposure time and careful processing, patterns emerge. The universe becomes a data archive of its own history. Hubble deep fields did something similar in visible and near-infrared light. They pointed at apparently empty regions of sky and gathered light for many orbits. The result changed the emotional scale of astronomy. Empty sky became crowded with galaxies. The lesson was not that every dark patch is visually spectacular to the eye. The lesson was that faint light, accumulated patiently, reveals structure far beyond ordinary perception. A telescope does not make the universe large, it makes the largeness measurable. Radio astronomy adds a different kind of reach. Radio waves pass through dust that blocks visible light. They reveal cold hydrogen, molecular gas, pulsars, quasars, cosmic microwave background radiation, and jets from active galactic nuclei. A radio dish turning under the sky may look slow, almost mechanical in a plain way, but it can detect processes happening across billions of light years. Interferometers combine signals from dishes separated by large distances, making a virtual telescope far larger than any single instrument. The image of a black hole shadow and the mapping of distant gas both depend on timing, calibration, and patience. X-ray observatories show the hot universe, galaxy clusters filled with plasma, accretion disks around compact objects, supernova remnants, neutron stars, black hole environments, and shock fronts where clusters collide. Ultraviolet telescopes trace young stars and hot gas. Gamma-ray detectors catch violent events and high-energy particles. Infrared telescopes see through dust and reveal cool objects. Optical telescopes show stars, galaxies, nebulae, and lenses. No single wavelength reveals the universe entire. The observable cosmos is assembled from overlapping maps, each one sensitive to a different physical process. Gravitational waves opened another path. They are not light. They are ripples in spacetime produced by accelerating masses detected on Earth as tiny changes in distance inside instruments with long arms and precise lasers. The first confirmed gravitational waves came from merging black holes. Later detections included neutron star mergers, which also produced electromagnetic light. These signals do not enlarge the observable universe in the same way light does, but they provide a new messenger. They show that the cosmos can be measured through gravity directly, not only through photons. Neutrinos also carry information from places light struggles to escape. Solar neutrinos reveal nuclear reactions in the sun's core. Supernova neutrinos can arrive from a collapsing star before some light escapes. Cosmological neutrino backgrounds are predicted from the early universe, though far harder to detect directly. Each messenger has its own horizon, its own limitations, and its own value. To ask how big the universe is means asking what kinds of signals can reach us, and what those signals can still remember after crossing billions of years of expanding space. The observable horizon has layers. The particle horizon marks the maximum distance from which signals could have reached us since the beginning of the universe. Under the expansion history we infer. The cosmic microwave background is the oldest light we can see directly, because before it the universe was opaque to photons. The event horizon is different. It marks the boundary beyond which light emitted now will never reach us in the future, because accelerated expansion carries regions away too quickly. The universe has not only a past limit of observation, but also a future limit of contact. Accelerated expansion changes the long future of cosmic visibility. Galaxies outside our gravitationally bound neighborhood will, over immense timescales, become more redshifted, dimmer, and harder to observe. Their light will stretch to longer wavelengths, their clocks will appear to slow. Eventually, many will fade beyond practical detection. The local group, or the merged descendant of the Milky Way and Andromeda, may become an island of stars in a much darker observable sky. This is not happening on human timescales, but it is part of what dark energy means for cosmic size. The universe was not always dominated by dark energy. In the early universe, radiation mattered more. Later, matter dominated the growth of structure. Only in more recent cosmic history did dark energy become the dominant component of the expansion. That changing balance affects how large the observable universe is today. Gravity slowed expansion for a time. Dark energy now accelerates it. The light we receive has crossed a cosmos whose behavior changed while the photons were traveling. Distance is therefore a historical quantity, not just a present location. When cosmologists say the observable universe has a radius of about 46 billion light-years, they are usually speaking of a present comoving distance. That is where the matter that emitted the oldest observable light would be now, if we assign coordinates that expand with the universe. At the time the cosmic microwave background photons were released, the physical distance to that matter was much smaller. Since then, space expanded enormously. The light has moved toward us the whole time, while the distance scale itself grew. The photon journey and the changing ruler must be understood together. This is why the edge of the observable universe is not an edge in the ordinary sense. There is no cliff where galaxies stop. There is no final star. The horizon is more like the edge of what the past has delivered. Beyond it, light may still be traveling toward us, but has not had enough time to arrive, or the expansion history may prevent some signals from ever reaching us. Regions beyond the horizon may contain galaxies, clusters, voids, and cosmic web structures, much like the ones we can map. Current evidence suggests the universe continues beyond what we see, but how far is unknown. The entire universe could be infinite. It could be finite but so large that the observable part is only a tiny fraction. It could have a topology that wraps around in ways difficult to detect, though observations constrain many simple possibilities. Its spatial curvature appears very close to flat, within current measurement limits, but flatness does not by itself prove infinity. A very large finite universe can look flat locally, just as a small patch of Earth's surface looks flat to someone standing on it. The observable universe may be a local patch of something much larger. Curvature is measured through geometry. In a positively curved universe, parallel lines would eventually converge in a global sense, like paths on a sphere. In a negatively curved universe, they would diverge more than expected. In a flat universe, Euclidean geometry holds on large scales. The cosmic microwave background helps test this by comparing the observed angular size of known early universe patterns with predictions. So far, the result is very close to flat. But very close to flat does not answer whether the total universe is infinite or only beyond our measuring range. Topology asks a different question: how space is connected. A video game world can wrap around so that leaving one edge brings you back from the other, while still feeling flat inside the game. Some cosmological models ask whether the universe could have a repeating topology on enormous scales. Astronomers have searched for repeated patterns in the cosmic microwave background, matching circles or duplicated structures that might reveal light traveling around a finite cosmos. No convincing evidence has emerged. If the universe has such a topology, the scale may be larger than the region we can observe. The word infinite should be handled carefully. Infinity is not just very large, it is not a big number. If space is truly infinite, there are no edges at any distance. There may be endless galaxies, endless regions beyond our horizon, perhaps endless repetitions of conditions if matter configurations repeat over enough space, though such ideas depend on assumptions far beyond direct evidence. Cosmology can allow infinity mathematically, but observation can only test the finite region from which signals have reached us. Science can say the universe may be infinite. It cannot measure all of infinity. A finite universe, on the other hand, does not need an edge. The surface of Earth is finite in area, but has no edge on the surface itself. A traveler going straight long enough returns to the starting point, not by reaching a boundary, but by following a curved geometry. Higher dimensional analogies are difficult, and they should not be mistaken for direct pictures, but they show how finite can differ from bounded. The universe could be finite without having a wall. It could be unbounded in ways our minds do not easily picture, because we evolved inside small, nearly flat environments. The size of the observable universe is therefore the part of the question we can answer most clearly. The size of the entire universe remains unknown. This is not a failure of curiosity. It is a consequence of physical limits. We cannot receive information from regions whose light has not reached us. We cannot build a telescope that sees around the horizon by collecting more photons, because the missing photons are not here. A larger mirror can detect fainter things within the observable universe. It cannot collect light that has not arrived. There are indirect clues, but they remain indirect. If the whole universe were much smaller than the observable universe in a wrapped topology, repeated patterns might appear. If curvature were strongly positive or negative, the cosmic microwave background would reveal it. If inflation occurred, it could have stretched the universe far beyond the observable horizon, perhaps making our visible region a tiny smooth patch. But different models can fit current data. The unobservable part cannot be confidently mapped by imagination. It can only be constrained by what the observable part tells us. The first mental scale of the observable cosmos is a sphere around us with a radius of about 46 billion light-years. The volume of such a sphere is so large that ordinary comparisons collapse. Even if galaxies were rare, the number would be vast. They are not rare on cosmic scales. Deep fields suggest hundreds of billions, perhaps up to 1 trillion or more galaxies in the observable universe, depending on definitions and faint populations. Many are small dwarf galaxies. Some are large spirals. Some are giant ellipticals. Many from early epochs are irregular, clumpy, and still assembling. Counting galaxies is not simple. Nearby galaxies can be resolved into stars. Distant galaxies blur into faint points. Some are hidden behind dust or lost in the brightness of foreground objects. Some are too faint for current telescopes. Surveys estimate the population by observing representative fields, correcting for selection effects, modeling galaxy evolution, and extrapolating below detection limits. The number is not a census where every galaxy receives a label. It is a statistical estimate built from limited views and tested against models of cosmic history. Stars are even harder to count. The Milky Way alone may contain hundreds of billions. A large elliptical galaxy can contain far more. Dwarf galaxies contain far fewer, but they are numerous. If the observable universe contains hundreds of billions of galaxies, then the number of stars is likely in the range of hundreds of sextillions or more, depending on the galaxy population and the average stellar mass. The exact number matters less than the fact that stars are a common product of cosmic evolution. Gravity turns gas into galaxies, galaxies into star-forming regions, and star-forming regions into stellar populations. Planets likely multiply that scale again. Exoplanet surveys show that planets are common around stars. Many stars have planetary systems. Some have compact systems of rocky worlds. Some have gas giants. Some have planets between the sizes of Earth and Neptune, a class common in the galaxy but absent from our solar system. Many worlds orbit too close to their stars for surface water. Others orbit in cold darkness. Some may have atmospheres stripped by radiation. Others may have deep oceans, thick hydrogen envelopes, or frozen crusts over salty interiors. The universe is not only big in empty distance, It is big in physical variety. Yet almost all of this variety is unreachable. The nearest exoplanets are several light years away. Most are hundreds or thousands of light years away. Their atmospheres are inferred from tiny changes in starlight during transits or from direct spectra in rare favorable cases. A molecule in a distant atmosphere may appear as a small absorption feature after many observations are combined and noise is removed. A planet can be real, massive, and complex, while existing for us as a dip in brightness, a wobble in a star, or a faint separation from glare. The scale of the universe turns worlds into signals. Galaxies at billions of light years are more remote still. We see their integrated light, the combined radiation of stars, gas, dust, black holes, and star-forming regions. A spiral galaxy in a telescope image may be hundreds of thousands of light years across, but at great distance it shrinks to a smudge. Spectra reveals star formation, chemical enrichment, gas motion, and redshift. Lensing can magnify background galaxies into arcs. Supernovae can briefly outshine their host galaxies. The enormous becomes faint because distance spreads light over vast areas before it reaches a detector. Surface brightness has its own cruelty. As the universe expands, distant objects become dimmer not only because they are far away, but because their light is redshifted, their arrival rate is slowed, and their apparent surface brightness fades strongly with redshift. This makes the early universe difficult to see, even with large telescopes. A galaxy from near cosmic dawn may be forming stars intensely, yet appear as a weak infrared source. Its details are blurred by distance, stretched by expansion, and filtered by intervening gas. Observing the early universe is not simply a matter of looking harder. It is a matter of extracting faint evidence from physical limitations. Gravitational lensing helps. A massive galaxy cluster can bend spacetime enough to magnify and distort galaxies behind it. In deep images, background galaxies appear as arcs, streaks, and duplicated images around the cluster. The lens is not glass. It is mass, visible galaxies, hot gas, and dark matter together, shaping the path of light. Lensing can reveal objects too faint to detect otherwise, but it also complicates interpretation. Astronomers must model the mass distribution of the lens to reconstruct the source. The universe sometimes provides a telescope made of gravity, but it does not provide easy instructions. The bullet cluster and similar systems show dark matter through separation. In a collision between galaxy clusters, hot gas interacts and slows, while galaxies and dark matter pass through more easily. X-ray maps show the hot ordinary matter. Gravitational lensing maps show where most of the mass lies. The offset provides evidence that much of the mass is not in the hot gas. This does not identify dark matter particles, but it strengthens the case that unseen gravitating matter exists. On scales of clusters and cosmic structure, the universe is larger than the light alone would suggest. Galaxy rotation curves tell a similar story on smaller scales. Stars and gas in the outer parts of many galaxies orbit too quickly to be explained by visible matter alone under ordinary gravity. Vera Rubin and colleagues helped establish this pattern in the 20th century. The simplest interpretation in the Standard Model is that galaxies sit inside extended halos of dark matter. These halos reach far beyond the visible disks. A galaxy's true gravitational size is therefore larger than its starlight. The cosmic web is shaped largely by matter we do not see directly. Dark matter made the early universe clump more effectively. Ordinary matter was coupled to radiation before recombination, but dark matter could begin forming gravitational wells earlier. After the universe became transparent and ordinary matter cooled, gas fell into those wells, eventually forming stars and galaxies. Simulations using cold dark matter reproduce many large-scale features of the observed cosmic web. They are not perfect in every detail, especially on small galactic scales, but they show why dark matter is not an optional decoration. It is central to how a universe this structured emerged from tiny early fluctuations. Simulations also teach humility. A supercomputer can evolve billions of particles under gravity and hydrodynamics, adding prescriptions for star formation, black hole feedback, supernova heating, cooling gas, and chemical enrichment. The result can look strikingly like galaxy surveys, with filaments, clusters, voids, and evolving galaxies. But every simulation depends on assumptions. Subgrid physics stands in for processes too small to resolve directly. When simulations match observations, they strengthen a model. When they fail, they show where physics is missing or simplified. The universe cannot be replaced by a simulation, but simulation helps interpret its scale. The cosmic web did not appear all at once. Early density differences grew slowly. Gas collected in dark matter halos. The first stars formed, lived briefly, and exploded, enriching their surroundings with heavier elements. Galaxies merged. Black holes grew at their centers. Clusters assembled. Voids expanded as matter drained toward denser regions. Over billions of years, gravity turned a nearly smooth early universe into a structured one. The observable cosmos today is a time-sliced mixture, nearby galaxies seen in their recent state, distant galaxies seen young, and the cosmic microwave background seen as an infant pattern. This mixture makes cosmic maps strange. A map of the sky is not a single present moment. The moon is 1 second old. The sun is 8 minutes old. The center of the Milky Way is tens of thousands of years old. Andromeda is 2.5 million years old. Distant quasars are billions of years old. The cosmic microwave background is almost the age of the universe. Looking outward is looking backward, and looking far enough reveals epochs that no longer exist in the same form. The observable universe is not just a region of space. It is a layered archive of time. Quasars show that archive sharply. Powered by supermassive black holes accreting gas, quasars can outshine entire galaxies and be visible across enormous distances. Many were more common when the universe was younger, when galaxies had more gas and black holes were growing rapidly. A quasar spectrum can show emission lines shifted far into the red, absorption from intervening gas clouds, and evidence of chemical enrichment. Some quasars illuminate the matter between galaxies like background lamps. Their light carries information about the universe along the path, not only about the source. The intergalactic medium is not empty. It contains thin gas spread between galaxies, shaped by gravity, radiation, and cosmic expansion. In the spectra of distant quasars, intervening hydrogen clouds leave absorption lines called the Lyman alpha forest. Each line marks gas at a different redshift between the quasar and Earth. The forest reveals how matter is distributed across cosmic time. It is a delicate way of measuring the universe, not by photographing every cloud, but by seeing how invisible gas removes specific wavelengths from a beam of ancient light. Cosmic distance is therefore not one number, but a set of relationships. A photon has a travel time, its wavelength has a redshift, its source has a present-day distance under a model. Its brightness gives a luminosity distance. Its apparent size gives an angular diameter distance. At high redshift, angular diameter distance behaves counterintuitively. Beyond a certain point, very distant objects can appear larger in angular size than a simple non-expanding universe would suggest, because the light was emitted when the universe was smaller. The geometry of expansion changes the way the sky translates into distance. This is why a universe can be 13.8 billion years old and have an observable diameter around 93 billion light-years. The oldest light did not start 46 billion light-years away in the ordinary sense. It started from matter much closer to the matter that would become our region, while the universe was smaller and hotter. The photons traveled as space expanded, and the matter that emitted them is now far away in comoving coordinates. The observable diameter is a present-day measure of an expanding history. Without expansion, the number would be different. With expansion, it becomes the scale we infer. No spacecraft can travel to the edge of the observable universe. The edge is not a destination waiting at a coordinate. Even if a spacecraft could move near the speed of light, cosmic expansion and the finite age of the universe would keep much of the horizon unreachable. Human probes have barely crossed the heliopause into interstellar space. Voyager signals arrive weekly after traveling for hours, not billions of years. The entire record of spacecraft exploration is a small movement inside one stellar neighborhood. Cosmology reaches farther because light has already made the journey. The largest telescopes are therefore time machines only in the limited sense that they collect old light. They do not change the past. They do not open portals. They receive photons that have survived long journeys through expanding space, past gas clouds, gravitational fields, and foreground galaxies. A telescope mirror is a physical object with temperature, alignment, dust contamination, calibration errors, and finite collecting area. Its power comes from accumulating evidence. The more ancient the light, the more careful the interpretation must be. Data reduction is part of the story. Raw telescope images contain cosmic ray hits, detector noise, thermal signatures, scattered light, dead pixels, distortions, and foreground contamination. Astronomers subtract backgrounds, align exposures, calibrate wavelengths, correct flat fields, and compare results with simulations. The final image may look clean, but its cleanness is earned. This matters because the universe at great distance is faint. A claimed early galaxy, a weak lensing signal, or a subtle absorption feature can depend on understanding the instrument as much as understanding the sky. Spectroscopy often decides what an object is. A red point in an image might be a very distant galaxy, a dusty near galaxy, a cool star, or an artifact. A spectrum can reveal emission lines, breaks in the continuum, or absorption features that identify redshift and composition. Spectroscopic confirmation is difficult for the faintest objects, but it is essential when claims reach toward the earliest galaxies. The edge of observable cosmic history is not a clean line in an image. It is a frontier of signal-to-noise ratios, calibration, and repeated observation. The same caution applies to the cosmic microwave background. The CMB is ancient, but the sky between it and us is full of foregrounds, emission from the Milky Way, dust, synchrotron radiation, point sources, and instrumental effects. Missions observe at multiple frequencies to separate components. Polarization measurements are even more delicate. Searches for primordial gravitational wave signatures in CMB polarization require extraordinary care because galactic dust can mimic or obscure the signal. The oldest light is available, but it is not handed to us without interference. Our observable universe also changes as time passes. More light from very distant regions reaches us, so in that sense the particle horizon grows. But accelerated expansion means some regions we can see today are already beyond our future reach in practical communication terms. Light emitted by us now will never reach many galaxies we currently observe. The cosmos is visible in one way and unreachable in another. This distinction is not intuitive, but it follows from the expansion history. Seeing something does not mean being able to affect it or receive future messages from it indefinitely. The scale of the universe is often described with comparisons, but most comparisons fail. If Earth were a grain of sand, the Sun would be a larger grain a short distance away, but the nearest stars would still be separated by kilometers in the model, and the galaxy would cover enormous distances. If the Milky Way were the size of a city, the observable universe would still reach far beyond continents in that scaling. Every analogy begins usefully and then collapses. That collapse is part of the point. The universe is not built to fit human intuition. A better approach is to let each scale remain itself. The Earth-Moon system is a light-second system. The inner solar system is a light-minute system. The outer planets are light-hour worlds. The nearest stars are light-year distances. The Milky Way is a 100,000 light-year system. The local group is millions of light-years wide. Clusters and filaments are tens to hundreds of millions of light-years. The observable universe is tens of billions of light-years in radius. Each step is not just a bigger number, it is a different kind of physical environment. Inside the solar system, gravity from the sun dominates, and spacecraft trajectories can be calculated with exquisite precision. Inside the galaxy, stars orbit a shared gravitational potential shaped by visible matter and dark matter. Inside clusters, galaxies move through hot plasma and dark matter halos. On the scale of the cosmic web, expansion competes with gravity, and only the densest regions remain bound. On the scale of the observable universe, the expansion history itself becomes the subject. The question of size changes meaning as the scale increases. Cosmic time adds another layer. The universe was not filled with mature galaxies from the beginning. The first stars likely formed from hydrogen and helium, with almost no heavier elements. They may have been massive and short-lived, though details remain uncertain because none have been observed directly. Their deaths enriched later gas. Later generations of stars formed planets from heavier elements. The Sun formed about 4.6 billion years ago, long after the universe had already built galaxies, clusters, and many cycles of stellar birth and death. We live late enough for chemistry to be rich, but not late in the full possible life of stars. Red dwarf stars can burn for hundreds of billions or even trillions of years, far longer than the present age of the universe. The cosmos may remain capable of hosting starlight for a very long future, though star formation will gradually decline as gas is used up, heated, or locked away. In that long view, the current universe is not old in every sense. It is old enough to contain galaxies, planets, and life on at least one world. It is young compared with the possible lifetimes of its smallest stars. Size and age both depend on the clock being used. The observable universe contains matter at many stages of that clock. Some galaxies are young in the images because we see them as they were near cosmic dawn. Some nearby dwarf galaxies contain ancient stars and little current star formation. Some starburst galaxies are turning gas into stars rapidly. Some elliptical galaxies are dominated by old red populations. Some black holes are feeding, others are quiet. Because light travel time mixes epochs, a deep survey is like a museum arranged by distance instead of by room. The farther cases hold older exhibits. There is no single visual appearance of the universe. To human eyes from a dark site, the sky shows stars, a soft Milky Way band, a few planets, perhaps Andromeda, perhaps the Magellanic Clouds from southern latitudes. Through optical telescopes, galaxies and nebulae appear faint. Through processed images, color reveals structure beyond natural perception. Through radio maps, the sky glows with hydrogen, synchrotron emission, and the cosmic microwave background. Through simulations, matter becomes a web. Each view is true in its own wavelength or model. None is the whole. The phrase observable universe can also mislead because not everything within it is actually observable with present instruments. Some objects are too faint, too cold, too small, too obscured, or too distant for current detection. The observable universe means the region from which information could in principle have reached us, not the complete catalog of everything inside that region. There may be countless rogue planets, cold asteroids, black holes, dust clouds, faint dwarf galaxies, and low-surface brightness structures within our horizon that we have not detected. The horizon is a physical limit. Instruments impose smaller practical limits inside it. Low-surface brightness galaxies are a good example. A galaxy can be large and diffuse, with starlight spread so thinly that it is hard to distinguish from the sky background. Better detectors and survey methods have revealed populations that earlier catalogs missed. The universe did not gain those galaxies when we found them. Our inventory improved. This has happened repeatedly in astronomy. New wavelengths, longer exposures, larger surveys, and better analysis turn apparent emptiness into structure. The known universe grows not because the cosmos expands into awareness, but because observation becomes more capable. Cosmic expansion itself was once a discovery of that kind. Before the 20th century, the Milky Way was often treated as the whole stellar system. The nature of spiral nebulae was debated. Cepheid measurements showed that Andromeda lay far outside the Milky Way. Galaxy redshifts revealed expansion. The cosmic microwave background revealed a hot early state. Supernovae revealed acceleration. Each discovery enlarged not only the measured size of the universe, but the kind of universe scientists thought they were inhabiting. The modern observable cosmos is the result of many corrections to smaller pictures. The Milky Way once seemed large enough to be everything. Then, it became one galaxy among many. Galaxy clusters seemed enormous. Then, they became knots in a web. The observable universe now seems almost beyond comprehension, but it may still be a local region of a far larger whole. This pattern does not prove that every future answer will be larger. It only cautions against mistaking the edge of measurement for the edge of reality. Astronomy has repeatedly found that the universe extends beyond the first boundary people imagined. Still, caution cuts both ways. It is tempting to say that beyond the observable universe there must be infinite copies of everything, or multiverses, or realities with different physics. Some theories allow such possibilities. Inflationary models can lead to enormous regions beyond our horizon. Quantum cosmology and speculative frameworks raise further ideas. But none of these should be treated as established observations. The honest answer is narrower and stronger. The observable universe is about 93 billion light-years across, and the whole universe is larger, perhaps vastly larger, but its total size is not known. That statement may feel unsatisfying because it does not close the question. Science often becomes most trustworthy when it refuses closure it has not earned. The universe has a measurable horizon. The entire universe does not yet have a measured diameter. Models can estimate, constrain, or speculate, but no observation gives a reliable total size. The absence of an answer is itself information. It tells us where physics places the boundary between evidence and imagination. If the entire universe is infinite, then the observable universe is an island of information in an unlimited sea of space. If the entire universe is finite but much larger than what we see, then our observable region is still a small sample. If it is only slightly larger than what we see, there might be signatures waiting in the data, though none have been confirmed. Each possibility changes the meaning of cosmic size. None changes the scale of what is already visible, a sphere tens of billions of light-years in radius, filled with galaxies, clusters, filaments, radiation, and time. The cosmic microwave background provides the most distant electromagnetic surface, but there may be information from earlier times in forms other than light. Primordial gravitational waves, if detected, could reveal processes from inflation or other early epochs. The cosmic neutrino background, predicted from the early universe, would come from even earlier than the CMB, but detecting it directly is far beyond current capability. These messengers would not necessarily show a larger spatial universe, but they would let scientists probe earlier times. The horizon of knowledge has more than one dimension. The CMB also shows that the observable universe was once causally puzzling. Regions on opposite sides of the sky have nearly the same temperature, even though in a simple non-inflationary picture they would not have had time to exchange information. Inflation was proposed in part to solve this horizon problem by stretching a once-connected region to enormous size. If inflation occurred, the whole universe may be vastly larger than the observable part. The smoothness of the CMB is therefore both a measurement and a clue that our visible horizon may be a small piece of a larger expanse. The flatness problem points in the same direction. The universe appears very close to geometrically flat. Without a mechanism like inflation, early curvature would need to be finely tuned to produce the flatness observed today. Inflation can drive curvature toward flatness in the observable patch, much as a small patch on a huge sphere looks flat. This does not prove inflation in every detail, but it explains why cosmologists take the ideas seriously. The shape and size of the universe are tied to the physics of its earliest moments. There are also limits from the absence of certain patterns. If the universe were small enough for light to circle around and show us the same structures in different directions, astronomers might find repeated images of galaxy clusters or matching circles in the CMB. Searches have not found convincing evidence for such repetitions. This pushes the possible wraparound scale larger than the observable region for many topologies. Again, the conclusion is not that the universe is infinite. It is that if space wraps around, it does so on a scale too large for current observations to reveal clearly. The edge of the observable universe moves in a technical sense as time passes, but not in a way anyone can watch like a sunrise. New light from regions just beyond the previous horizon can arrive, carrying information from earlier states. At the same time, accelerated expansion means that many sources will become less accessible over the long future. The horizon is a dynamic concept embedded in cosmic history. It is not a fixed glass sphere. It is a boundary defined by paths light can take through spacetime. One of the strangest consequences is that some galaxies we see today can never receive a message sent from Earth now. They are visible because their old light is arriving, but their present separation and the expansion between us mean our new signal will never catch up. Observation does not imply mutual contact. The universe can show us a galaxy that is already beyond future communication. This is not science fiction. It is a feature of accelerated expansion in the standard cosmological model. The phrase "beyond the observable universe" should not be imagined as a darker zone outside a bubble. From the point of view of a galaxy beyond our horizon, its local universe may look ordinary. It may have stars, planets, clusters, microwave background radiation, and its own horizon. We are beyond the observable universe of some places just as they are beyond ours. The boundary belongs to observers. It is not painted onto space. The cosmos does not know that Earth is using this particular horizon as a measure. Earth's position is ordinary in some ways and special in others. It is ordinary because it is not the center of cosmic expansion. The laws of physics appear similar in distant galaxies. Large-scale observations show no evidence that our location occupies a privileged cosmic center. It is special because it is where our instruments are, where our samples exist, where life arose to ask these questions. Astronomy is performed from one planet, inside one solar system, through one atmosphere, or from machines launched above it. Every cosmic map carries that local origin. The atmosphere both protects and obscures. It blocks much ultraviolet light, most X-rays, gamma rays, and parts of the infrared. That is good for life and difficult for astronomy. Space telescopes exist partly because Earth is not transparent to all the messengers the universe sends. Ground-based observatories use high mountains, dry deserts, adaptive optics, radio arrays, and careful calibration. Space observatories use stable cold environments, unobstructed wavelengths, and long integrations. The size of the universe is measured through a partnership between earthbound patients and machines placed beyond the air. A CCD detector or infrared array does not understand awe. It counts photons. A spectrograph disperses light by wavelength. A radio receiver records voltage changes. A gravitational wave detector measures changes smaller than a proton across kilometers of instrument. Humans later interpret the patterns. The emotional force of cosmic scale comes after the measurement, not before it. This is why the most powerful descriptions of the universe often begin with something plain. A line in a spectrum, a faint source in a frame, a calibration file, a set of coordinates, a number in a table. The number 13.8 billion years comes from multiple lines of evidence, especially the cosmic microwave background combined with the standard model, along with other measurements of expansion and old stellar populations. It is not a guess made by looking at the oldest star. It is a reconstruction of cosmic history. The uncertainty is small compared with the age itself, though details of parameters remain actively studied. The universe is old enough for light to cross billions of light years, but expansion makes the current observable radius much larger than that age in light years. The distance to the CMB is not measured by parallax or by sending a signal. It is inferred through cosmology. The redshift of recombination is about 1100, meaning the universe has expanded by a factor of roughly 1100 in scale since that light was released. The photons arriving now have wavelengths stretched into microwaves. The matter that emitted them is not a visible shell of galaxies at the edge. It has evolved into structures far away, beyond direct observation in its present state. We see its ancient radiation, not its modern face. A galaxy at high redshift is different because we see starlight from matter that had already formed stars by then. The CMB comes from before stars, before galaxies, before planets, before heavy elements became common. It is the background against which later structure emerged. In maps, the CMB covers the whole sky, but after foreground subtraction it shows fluctuations too small to see without precise instruments. Those small differences became everything large. The largest structures in the present observable universe began as tiny departures from smoothness. Those departures grew through gravity, but growth was not instantaneous. Ordinary matter had pressure, radiation, shocks, cooling, and feedback. Dark matter clumped under gravity. Gas fell inward, heated, cooled, and formed stars. Supernovae pushed gas outward. Black holes injected energy. Galaxies merged and changed shape. The cosmic web is the result of many processes layered across billions of years. The observable universe is large enough that no single process explains every part. Expansion sets the stage. Gravity builds the framework. Astrophysics fills it with detailed behavior. Large-scale structure surveys are now so extensive that they measure not only where galaxies are, but how their distribution preserves the imprint of early universe sound waves. Baryon acoustic oscillations appear as a preferred separation scale in galaxy clustering. This scale acts like a ruler stretched by cosmic expansion. Comparing it at different redshifts helps trace how the universe expanded over time and how dark energy behaves. A pattern from the first few 100,000 years becomes a tool for measuring billions of years of history. Weak gravitational lensing provides another approach. The shapes of distant galaxies are subtly distorted by the gravity of matter between them and us. Individual distortions are tiny and buried under the galaxy's own shapes, but statistically, across millions of galaxies, a lensing map emerges. That map traces the distribution of matter, including dark matter. It is a difficult measurement, sensitive to telescope optics, atmospheric effects, galaxy modeling, and calibration. But it is powerful because it maps mass directly through gravity rather than relying only on light. Future surveys from missions and observatories such as Euclid, the Vera C. Rubin Observatory, the Nancy Grace Roman Space Telescope, and others are designed to improve these maps. They will not reveal the whole universe beyond the horizon, but they can refine the expansion history, the growth of structure, the behavior of dark energy, and the distribution of dark matter within the observable region. The known cosmos is large enough that even surveying a fraction of it produces decades of work. The unknown beyond it remains inaccessible, but the boundary inside the horizon can still sharpen. The observable universe is sometimes described as containing about 2 trillion galaxies, sometimes hundreds of billions, depending on the study, wavelength, and assumptions about faint galaxies. This range is not a contradiction so much as a reminder that counting faint things across cosmic time is difficult. A small dwarf galaxy at high redshift may be invisible to one survey and inferred statistically by another. As telescopes improve, the census changes. The universe's physical size does not change because estimates improve, but our inventory of what fills that size does. The farthest confirmed galaxies are not stable trophies. Records change as observations improve, and some candidates are revised when better spectra arrive. A photometric redshift can suggest extreme distance, while spectroscopy can confirm or overturn it. This is normal science. The edge of the known galaxy population is built from candidates, confirmations, corrections, and debate. The desire to find the farthest object is understandable, but the more important work is understanding the population, how early galaxies formed, how quickly they grew, how they produced light, and how they changed the gas around them. Cosmic reionization is one of those population questions. After recombination, the universe contained mostly neutral hydrogen. The first stars, galaxies, and accreting black holes produced ultraviolet radiation that gradually reionized this gas. Observations of distant quasars, galaxy spectra, and the CMB constrain when and how this happened, but details remain active research. Reionization marks a transition from the dark ages to a transparent intergalactic medium at many wavelengths. It is not the edge of the universe, but it is a major change in what could be seen and how light traveled. When we look at a very distant galaxy, we may be seeing it during or near this era, when the intergalactic medium was changing. The light may be absorbed by neutral hydrogen, shifted by expansion, magnified by lensing, and contaminated by foregrounds. Extracting the galaxy's properties requires models of stars, dust, gas, metallicity, and age. A small red mark in a deep image may represent a system forming stars in a universe less than a few % of its current age. The scale is immense, but the evidence often arrives as a few pixels and a spectrum. Black holes also appear across cosmic time in a way that challenges formation models. Some quasars powered by massive black holes existed when the universe was less than 1 billion years old. Growing such black holes so quickly requires massive seeds, efficient accretion, dense environments, or combinations still being studied. These objects do not change the measured size of the universe, but they show that complexity developed early. The observable cosmos is not only large, it became structured quickly enough to produce extreme objects while still young. The growth of black holes connects small and large scales. Gas falling into a supermassive black hole can release enormous energy, driving winds and jets that influence the host galaxy. Feedback from active galactic nuclei may heat gas, regulate star formation, and shape galaxy evolution. On cluster scales, jets inflate cavities in hot plasma. On cosmic scales, black hole growth traces the history of galaxies and gas supply. A point like quasar in a deep field is therefore not just a bright dot. It is a clue about matter, gravity, and energy in the young universe. Neutron stars and stellar mass black holes reveal another side of scale. They are tiny compared with galaxies, but their mergers can be detected across immense distances through gravitational waves. A neutron-star merger can forge heavy elements and produce light across the electromagnetic spectrum. The signal from such an event is a timestamp, a distance estimate, a test of gravity, and a piece of cosmic chemical history. The universe is large enough that rare events happen often somewhere, yet distant enough that each event arrives as a faint trace. Supernovae built the distance ladder and revealed cosmic acceleration. Type 1a supernovae are especially important because their light curves can be calibrated, making them useful for measuring distances to far galaxies. In the 1990s, observations showed that distant Type 1a supernovae were dimmer than expected in a decelerating universe, pointing to accelerated expansion. That result led to dark energy as a central part of modern cosmology. A dying star in a distant galaxy became evidence about the fate and size of the universe. The acceleration does not mean galaxies inside clusters are being torn apart by expansion. Bound systems remain bound. The Milky Way is not expanding internally because dark energy stretches the universe. The solar system is not growing. Atoms are not swelling. Expansion is visible over large enough distances where gravity has not bound objects together. This distinction prevents a common misunderstanding. Cosmic expansion is not a force pulling every object apart equally. It is the evolution of large-scale distances in the space-time geometry described by general relativity. On the largest scales, the future depends on dark energy's behavior. If it is a cosmological constant, expansion continues accelerating, galaxies beyond the local group fade. Star formation declines, and the universe becomes colder and emptier over immense times. If dark energy changes with time, other futures are possible, though constrained by observations. Some speculative scenarios are dramatic, but current evidence supports a more restrained picture of ongoing acceleration. The fate of the universe remains tied to the same measurements that determine its size. Cosmic horizons also affect the far future of astronomy. In a universe dominated by accelerated expansion, future observers in the merged local group may not see distant galaxies as we do. The evidence for expansion could become harder to access if other galaxies fade beyond detection. They might still have local records, old stars, background radiation stretched to extremely long wavelengths, and theoretical clues, but the sky would be poorer in external evidence. We live at a time when the universe is old enough to be structured and young enough that distant structure remains visible. This timing is not a cosmic gift arranged for us. It is simply the era in which Earth exists. Had life arisen much earlier, heavy elements and stable planetary systems might have been less common. Had it arisen far later, many distant galaxies might be harder to see. The observable universe is partly a function of when observers appear. The same laws allow different skies at different cosmic ages. The size we measure is therefore the size of our observable cosmos at this time, from this location, with this expansion history. The cosmic microwave background will not remain equally easy to detect forever. As expansion continues, its wavelengths stretch and its temperature falls. In the far future, it may become so long wavelength and faint that detecting it against local foregrounds becomes extraordinarily difficult. Today, it is still a strong pillar of evidence. Microwave receivers can measure it. Satellites have mapped it. Its pattern remains legible. The universe still carries a readable trace of its hot early state across the sky. The observable universe also includes the relic neutrino background in theory, dark matter distributions in inference, and gravitational waves from many sources, known and unknown. Light is the main messenger, but not the only one. As detectors improve, the observable cosmos may become richer without becoming larger in the horizon sense. We may learn more about what happened inside the same vast sphere. We may refine parameters, discover new particles, detect new backgrounds, or resolve tensions. The boundary of evidence can deepen as well as expand. A useful way to imagine the observable universe is not as a bubble floating in darkness, but as a past light cone. Your position now is the point at the tip. All the light reaching that point traces paths backward through spacetime. Nearby events lie close to the tip. Distant events lie farther down the cone. The cosmic microwave background lies near the base of the electromagnetic view. Beyond that, light cannot show earlier times directly because the universe was opaque. This geometric picture is less intuitive than a sphere, but it is closer to how relativistic cosmology thinks. A past light cone also explains why no map is simply present tense. When a survey places galaxies in 3 dimensions, it is mapping them at different look-back times. Corrections and models can infer a present-day distribution under assumptions, but the direct observations are historical. A distant galaxy cluster is seen as it was billions of years ago. Its present condition is unknowable by direct observation right now. The light that would show its present state may not reach us for billions of years, or ever, depending on expansion. This delay applies to every direction, so the observable universe is a layered sphere of cosmic memory. The outer layers show younger cosmic epochs. The inner layers show more recent structures. The center is not a location of cosmic importance, only the observer's position. If we could move to another galaxy, the layers would rearrange around that location. Cosmology removes Earth from the center of existence while also placing Earth at the center of its own observable evidence. Both statements are true in different senses. The language of center and edge has caused confusion for as long as people have tried to picture expansion. If every distant galaxy seems to recede from us, it feels as if we are central. But observers in those galaxies would see the same pattern. Expansion in a homogeneous universe produces recession from every vantage point. The center is not in space. If the Big Bang has a center in the equations, it is in time, the earlier hot dense state from which all observed regions evolved. Asking where it happened misunderstands the model. It happened everywhere in the observable universe's past. This does not make the model mystical, it makes it geometric. General relativity describes how space-time evolves with matter and energy. The Friedmann equations describe expanding homogeneous universes under certain assumptions. Observations determine parameters. The result is a universe with no known central point in space, a finite age since the hot Big Bang, and an observable horizon set by light travel through expansion. The concepts are difficult, but they are not decorative. They come from equations tested against data. The difficulty is emotional as much as mathematical. Human beings are used to objects with edges, rooms, fields, islands, planets, maps. A universe without a known edge resists that habit. A universe with an observable edge that is not a physical edge resists it even more. The mind wants a final wall or a final answer. Cosmology offers a horizon and says that beyond it the same rules may continue. Or the whole geometry may be larger than we can test, but no photon has brought us the full answer. Even within the observable region, much is permanently historical. We cannot see the Milky Way from outside in the present. We infer its shape from inside the disk. We cannot watch Andromeda as it is now. We see it 2.5 million years ago. We cannot observe a distant galaxy's current state if its light takes billions of years to arrive. We build a coherent picture by combining local physics, distant observations, and models. The size of the universe is known not by standing outside it, but by reconstructing it from within. There is no outside vantage point available to astronomy. Every image is taken from somewhere inside the universe. Every detector is made of the same ordinary matter whose cosmic fraction is only about 5%. Every equation is tested by signals that reached this small region of space. This limitation is not a weakness to be hidden, it is part of the achievement. From one planet, using light, gravity, particles, and mathematics, scientists have measured a cosmic horizon tens of billions of light-years away. The achievement becomes more striking when you remember how little of the sky a deep field covers. A tiny dark patch, gathered for many hours, can contain thousands of galaxies. Multiply that across the whole sky, account for depth, correct for faintness, and the observable universe becomes crowded beyond ordinary language. But each multiplication must be done carefully. The sky is not uniform on small scales. Surveys have biases. Foregrounds interfere. The calculation is not a child's exercise in scaling up an image. It is a statistical reconstruction from many observations. Some regions of the sky are blocked by the Milky Way's disk, a zone of avoidance where dust and stars obscure distant galaxies in optical light. Infrared and radio surveys can see through some of this material, revealing structures hidden behind our own galaxy. Even the map of nearby large-scale structure has gaps that must be filled with multiple wavelengths and models. The observable universe surrounds us, but our own galaxy stands in the way of seeing parts of it cleanly. The local environment shapes the cosmic map. Cosmic variance adds another limit. We can observe only one universe, or more precisely, one observable realization of the universe. Statistical measurements of the largest scales are limited because there are only so many independent large regions within our horizon. If a pattern appears on scales comparable to the observable universe, it is hard to know whether it is a meaningful feature or a statistical fluctuation. Larger surveys cannot create more universe beyond the horizon. They can only measure the one available sky more carefully. This matters for anomalies in the cosmic microwave background, such as large-scale alignments, hemispheric differences, or cold spots that have been discussed for years. Some may be statistical accidents. Some may reflect foregrounds, systematics, or unknown physics. None has overturned the standard model on its own. The largest scales are where certainty is hardest, because there are few samples. When the universe itself is the experiment, there is no laboratory where the whole thing can be repeated. Despite those limits, the standard model works remarkably well. It explains why the CMB has the pattern it does, why galaxies cluster as they do, why light elements have their observed abundances, and why the universe's expansion history has its broad shape. A model with only a handful of parameters fits data from very different epochs and instruments. That success does not end inquiry. It makes the remaining tensions sharper. The better the model works, the more interesting the deviations become. The observable universe is therefore both measured and mysterious. Its diameter can be stated in one sentence, but understanding the statement takes a journey through light years, redshift, expansion, the CMB, dark matter, dark energy, galaxy surveys, and horizons. The number is not a slogan. It is the compressed result of a century of observations and theory. When someone says the observable cosmos is about 93 billion light years across, they are speaking in shorthand for an entire structure of evidence. A number that large can become meaningless if it is repeated too quickly. 93 billion light years means light crossing from one side of the observable region to the other in a static universe would need 93 billion years. But the universe is not static, and no light is crossing from one edge to the opposite edge as a simple measurement. The diameter is a present-day comoving scale. It describes the region around us whose past has become visible. Its meaning is bound to the history of expansion. If a galaxy near the edge of our observable universe emitted the light we now see when it was young, that galaxy's present light, emitted today, may never reach us. The older light arrived because it was emitted when conditions were different and distances were smaller in the relevant sense. The newer light may be carried away by expansion faster than it can make progress toward us over cosmic time. This is one of the hardest ideas in cosmology because it separates visibility from ongoing connection. The past can be seen even when the present is forever out of reach. The cosmic event horizon is not the same distance as the particle horizon. The particle horizon asks what we can see now from the past. The event horizon asks what events can ever send signals to us in the future. In a universe with accelerated expansion, the event horizon is much closer than the farthest matter we can currently observe in ancient light. Some regions are in our past light cone, but not in our future communication region. The universe is generous with old evidence and strict with future access. This has consequences for any imagined intergalactic travel or communication. Even if advanced civilizations existed in distant galaxies, cosmic expansion could place many beyond any possible exchange. Signals sent now would not arrive. Their old light might, revealing their galaxies as they once were. Science fiction often treats the universe as a large arena through which sufficiently advanced travelers can move. General relativity and dark energy make the arena more severe. Some distances are not merely difficult, they are causally closed in one direction. Within bound structures, the story is different. The Milky Way and Andromeda will merge despite cosmic expansion because they are gravitationally bound inside the local group. Nearby dwarf galaxies will continue interacting. Stars will orbit the merged galaxy. Planets will remain tied to their stars unless disturbed by local events. The expansion of the universe does not prevent local futures from unfolding. It isolates bound islands from one another over the longest times. The universe becomes more separated even as each island continues its internal history. The word observable also changes with technology. Galileo's observable universe included moons of Jupiter and stars invisible to the naked eye. 19th-century telescopes revealed nebulae, star clusters, and galaxies before their nature was fully understood. 20th century radio and space telescopes revealed the CMB, quasars, pulsars, X-ray sources, and gamma-ray bursts. 21st century observatories reveal exoplanet atmospheres, black hole shadows, gravitational waves, and early galaxies. The physical horizon is ancient, but the practical horizon keeps moving inward toward it. No instrument will remove every uncertainty. A larger telescope can detect fainter galaxies, but still faces cosmic variance. Better spectra can confirm redshifts, but not observe beyond photon decoupling with light. More precise CMB maps can constrain parameters, but not directly identify dark matter particles. Gravitational waves can reveal mergers, but not replace all electromagnetic information. Cosmology advances through combined partial views. The universe is too large, too old, and too physically layered for one method to dominate completely. This is why a good answer to the title has to be careful. The universe we can observe is about 93 billion light-years across. The universe as a whole is at least that large, and probably much larger. It may be infinite, it may be finite with no edge. It may have a topology too large to detect. Science has no reliable measurement of its total size. Those statements are less dramatic than claiming infinity as a fact. But they are more honest. The mystery survives because the evidence itself has a boundary. The boundary is not hopeless. It is productive. It forces cosmology to define terms, separate observation from inference, and test models wherever signals exist. The unknown total size of the universe does not make the observable universe vague. It makes the observable universe more precious as a dataset. Every galaxy survey, every microwave map, every lensing measurement, every supernova light curve, and every gravitational wave event adds detail to the one region of the cosmos available to us. Imagine a researcher opening an archive of deep-field data years after the observations were taken. The photons have already been collected. The files sit on servers. A source extraction algorithm identifies faint objects. A catalog lists positions, brightnesses, colors, uncertainties, flags. Some entries are stars. Some are galaxies. Some are artifacts. Some are too ambiguous to classify. The work is not cinematic in the usual sense. It is sorting, checking, calibrating, comparing, yet this is how the largest measurable structure in existence becomes known. In another room, a cosmologist runs a Markov chain, testing combinations of parameters against CMB data, baryon acoustic oscillations, supernovae, and lensing. The output is not a picture, but a probability distribution. A value for matter density, a value for the Hubble constant, a curvature constraint, an uncertainty range. These numbers will later become sentences about age and size. The quiet machinery of inference stands behind every simple public answer. The universe is translated into parameters before it becomes a story. In a desert, a spectrograph gathers light from thousands of galaxies at once through fibers or slits positioned with precision. Each galaxy produces a spectrum. Each spectrum yields a redshift if the lines are clear enough. Night after night, the survey grows. The map fills in. Clusters emerge. Filaments stretch. Voids open. No one is flying through the cosmic web. The web is being reconstructed from light that arrived at Earth after crossing distances so large that the galaxies changed while the light traveled. In a microwave map, the whole sky becomes a surface of slight temperature differences. The colors are artificial, chosen to make tiny variations visible. Without that exaggeration, the CMB would look almost the same everywhere. The universe's beginning, at least as light can show it, is not a scene of flames and shapes. It is a smooth glow with small statistical irregularities. Those irregularities are enough. Gravity had time. Matter fell inward. Stars formed. Galaxies assembled. The visible universe grew from differences so slight that they require sensitive instruments to display. The connection between the smallness of the fluctuations and the largeness of the result is one of the most important facts in cosmology. A variation of 1 part in 100,000 in the early radiation field became galaxy clusters, filaments, and voids across billions of light-years. The universe did not need large initial lumps to produce large structures. It needed gravity, dark matter, expansion, time, and small seeds. Scale emerged gradually. The present observable cosmos is the amplified pattern of an almost smooth early state. That amplification also means the universe is readable backward. Galaxy clustering today helps infer the initial conditions. The CMB helps predict later structure. Simulations connect the two. Supernovae and bow trace expansion between them. Weak lensing maps the growth of matter. When these independent threads agree, they form a coherent history. When they do not, scientists investigate. The size of the universe is not one measurement at the end of a ruler. It is a consistency check across cosmic time. The largest named structures, such as superclusters, walls, and quasar groups, sometimes appear in headlines as if they challenge cosmology by being too large. Some are real overdensities. Some depend on definitions and statistical thresholds. The cosmological principle does not forbid structure below the scale of homogeneity, and that scale is enormous. Scientists evaluate such claims by comparing surveys with simulations and by asking whether the structures are gravitationally bound, statistically unusual, or simply part of the expected cosmic web. Large does not automatically mean impossible. The local supercluster, Laniatea, and other flow-defined regions help describe the motions of galaxies near us. They are meaningful maps of local gravitational flows, but they are not solid objects with sharp borders. Their boundaries depend on how velocities are reconstructed. On larger scales, many of these regions are not gravitationally bound against cosmic expansion. This is another example of size-requiring definition. A galaxy has a luminous disk, a gas disk, a stellar halo, and a dark matter halo. A supercluster has looser boundaries. The universe requires careful nouns. Voids require the same care. A cosmic void is not an absolute vacuum. It is a region with far fewer galaxies than average. It can contain faint galaxies, dark matter, gas, radiation, and magnetic fields. Voids expand relative to denser regions as matter flows out toward filaments and clusters. They are important because they occupy much of the universe's volume. If you could place yourself in a void, the nearest bright galaxies might be far away, and the sky would look poorer. The universe's largeness is partly the largeness of its underdense spaces. The average density of the universe is extremely low by everyday standards. Spread over cosmic volumes, matter amounts to only a few atoms per cubic meter if translated roughly, though local densities vary enormously. A star is dense. A molecular cloud is thin by Earth standards but dense for space. A galaxy cluster contains hot gas thinner than any laboratory vacuum, but spread over millions of light-years. The universe can be almost empty in local sensation and still contain enough matter overall to shape its expansion and structure. Radiation fills the universe too. The cosmic microwave background photons are everywhere, hundreds per cubic centimeter, though each carries very little energy today. Starlight and dust reprocessed infrared light form extragalactic background light. High-energy backgrounds come from active galaxies and other sources. Neutrinos pass through matter almost untouched. Cosmic rays travel through magnetic fields. Space is not empty silence in a physical sense. It is filled with low-density matter, fields, radiation, and particles moving through enormous distances. Magnetic fields thread galaxies and clusters, though their origins and evolution remain active research. They influence charged particles, shape synchrotron emission, and interact with plasma. Their energy density is usually small compared with gravity on cosmic scales, but they matter locally. The universe is not merely gravity and expansion, It is plasma physics, nuclear physics, radiation transport, chemistry, turbulence, shock waves, and feedback. Scale does not erase detail. It multiplies the number of physical processes operating at once. The observable universe contains black holes across many masses, from stellar remnants to supermassive objects in galactic centers. It contains white dwarfs cooling slowly, neutron stars with crusts and magnetic fields, brown dwarfs too small for sustained hydrogen fusion, rogue planets moving without stars, cold comets in distant reservoirs, and dust grains drifting between stars. A map at the scale of billions of light years cannot show these objects individually, but they are part of the inventory. The cosmos is not only made of galaxies. Galaxies are containers for smaller histories. The Sun itself is an ordinary star in that inventory, not at the center of the galaxy, not among the first stars, not among the largest or smallest. Its ordinariness helps cosmology emotionally. The same physics seen in distant starlight operates here. Hydrogen fusion powers the Sun and other main sequence stars. Spectral lines identify elements across space because atoms behave consistently. Gravity shapes orbits from moons to galaxy clusters. Light travels with the same speed. The universe is measurable because physical laws appear stable across the observable region. If those laws changed dramatically with distance or direction, cosmology would be far more uncertain. Scientists test this by comparing spectra, fundamental constants, CMB patterns, nucleosynthesis, and the behavior of distant objects. So far, the evidence supports a universe governed by consistent physics on observable scales, though tests continue. This consistency allows a photon from a galaxy billions of light years away to tell us about hydrogen, oxygen, star formation, and motion. Without it, the observable universe would be a gallery of lights with no reliable translation. Cosmic scale also changes the meaning of now. In relativity, simultaneity across vast distances is not absolute in the simple way everyday life suggests. A galaxy's present state at a comoving distance of billions of light years is a model-dependent concept, not something directly observable. We can define cosmic time in the standard model because the universe is homogeneous and expanding, but no signal from that present state is available. The farther the object, the more the idea of what it is doing now becomes a calculation rather than an observation. This does not make distant galaxies unreal. It makes them part of space-time rather than objects in a single universal snapshot. Their past light is real. Their inferred evolution is modeled from physics and observations of similar galaxies at different distances. Their present state exists in the cosmological description, but it is not directly visible. The universe is too large for a universal live image. Every telescope frame is an intersection between our present and someone else's past. The scale of the universe also means that extinction, formation, and change are happening throughout the observable region at every moment in cosmic time, though we receive those moments delayed. Stars are being born in nearby molecular clouds. In distant galaxies, we see stars being born billions of years ago. Supernovae explode nearby and far away. Black holes merge. Gas falls into clusters. Planets form in disks. Civilizations, if they exist elsewhere, would be separated from us by the same light time and horizon limits. The universe is not static simply because it is too large to watch change quickly. When astronomers construct a timeline of the universe, they are compressing an immense variety of local histories into a broad sequence: inflation, hot plasma, nucleosynthesis, recombination, dark ages, first stars, first galaxies, reionization, galaxy growth, solar system formation, present acceleration. This timeline is useful, but it is not a single line experienced everywhere identically. Density varies. Galaxies form earlier in some regions and later in others. Local environments shape outcomes. The observable universe has a shared background history and countless local variations. The title asks how big the universe really is, and the word really carries weight. Really, the observable universe is about 93 billion light-years across. Really, the whole universe is not measured. Really, distance in cosmology is inseparable from time and expansion. Really, the most distant light is not from stars, but from the hot early plasma. Really, the edge we can see is not the edge of space. Really, most of the cosmic energy budget is in forms whose detailed nature remains unknown. Each of these statements corrects a simpler picture. A simpler picture might imagine Earth inside a sphere of galaxies with a hard surface. A better picture is a growing light cone inside an expanding space-time, filled with structures that formed from early fluctuations. The better picture is harder to draw, but more faithful. It allows ancient light from matter now far away. It allows horizons without walls. It allows galaxies to recede faster than light in expansion coordinates without breaking local physics. It allows a finite age and a larger present-day observable diameter. Cosmology requires giving up the wrong drawing before the numbers make sense. The wrong drawing is persistent because the night sky looks like a dome. Stars appear fixed on a surface. Constellations flatten distances into patterns. Ancient observers built myths and calendars from that appearance, and they were not foolish. The sky looks two-dimensional to the unaided eye. Telescopes, parallax, spectroscopy, and redshift turned the dome into depth. The transformation from sky as surface to universe as expanding spacetime is one of the deepest changes in human thought. It did not happen all at once, and it is still difficult to imagine. Even astronomers rely on visual tools that simplify. Logarithmic maps place the solar system, nearby stars, the Milky Way, neighboring galaxies, the cosmic web, and the CMB into one diagram by compressing each scale. Without logarithms, the diagram would be impossible. A linear map that showed Earth clearly could not fit the galaxy. One that fit the observable universe would make Earth vanish. Logarithmic thinking is one way the mind survives cosmic scale. It sacrifices ordinary proportion to preserve sequence. The observable universe has a radius of about 46 billion light-years, but almost all familiar structures occupy tiny fractions of that radius. The Milky Way's 100,000 light-year disk is about 1 part in hundreds of thousands of the observable radius. The local group is larger, but still minute. A galaxy cluster tens of millions of light-years across is vast and still small. A filament hundreds of millions of light-years long begins to feel cosmic, and yet it remains a feature inside the larger horizon. Scale stacks without mercy. Mercy is not a scientific property, but the phrase captures the mental pressure of the numbers. Each expansion of scale reduces the previous world. Earth becomes a planet. The solar system becomes a star system. The Milky Way becomes one galaxy. The local group becomes a small association. Clusters become knots. The cosmic web becomes texture. The observable universe becomes a horizon-limited patch. This reduction can feel diminishing, but it also connects every local object to a larger physical story. The atoms in a telescope mirror were made in stars or stellar explosions before being mined, refined, polished, and launched or mounted. The silicon in a detector came from cosmic chemical enrichment. The carbon in the people interpreting the data was forged in earlier generations of stars. Cosmology is not separate from local matter. The same universe being measured made the instruments that measure it. This reflection can become overly poetic if pushed too far. But the physical fact is straightforward: heavy elements are products of cosmic history. The universe's size also sets limits on probability arguments. With hundreds of billions of galaxies, rare events can happen many times. Rare planets, rare stellar systems, rare alignments, rare gravitational lenses, rare explosions, and rare evolutionary paths may still occur somewhere in the observable region. But rarity and distance work against detection. A phenomenon can be common enough to exist in many places and still be invisible to us, because it is faint, brief, obscured, or too far away. Large numbers do not automatically create accessible evidence. Alien life is one example, though it is not the center of this question. The observable universe likely contains enormous numbers of planets, but direct evidence for life beyond Earth has not been found. Biosignatures in exoplanet atmospheres are difficult to interpret. Radio searches cover limited parts of parameter space. Ocean worlds in our solar system require missions to test. Cosmic size makes life seem possible in many places, but size alone is not evidence. The universe can be vast and still require careful proof for every claim. The same discipline applies to multiverse ideas. A larger reality beyond our observable universe may be suggested by some theories, especially certain inflationary models, but direct evidence is lacking. The word universe itself becomes slippery in those discussions. Some use it to mean everything that exists. Others use it to mean our connected space-time region. For this script, the important distinction is simpler. The observable universe is measured. The entire universe is not. Anything beyond that must be labeled clearly as model or speculation. There is a quiet strength in that restraint. The observable cosmos is already large enough to exceed every intuitive measure. It does not need exaggeration. A single galaxy cluster contains more space than imagination can comfortably hold. A single deep field contains thousands of galaxies. The CMB comes from nearly the beginning of transparent time. Dark matter and dark energy dominate the cosmic accounting. The horizon lies tens of billions of light years away. The facts, stated plainly, are already overwhelming. A telescope continues gathering light regardless of whether the number feels overwhelming. Photons arrive one by one. A detector well fills. A readout records counts. A clock stamps the exposure. A guide star keeps the pointing steady. Later, the data become a calibrated frame. Somewhere in that frame may be a galaxy whose light began before Earth formed, or before the Milky Way settled into its current structure, or before most stars in the Sun's neighborhood were born. The vastness enters the archive quietly. On another night, a radio telescope measures the 21-centimeter line from hydrogen in a nearby galaxy, mapping rotation. On another, a survey telescope scans millions of galaxies for weak lensing. On another, a microwave instrument checks foregrounds. On another, a gravitational wave detector waits for a tiny strain. No single night answers the size of the universe. Together, over years and decades, the measurements build the answer we have: a large observable region, a consistent expansion history, and a total reality beyond current measurement. The answer also depends on the word big. Big in radius, about 46 billion light-years to the observable edge. Big in diameter, about 92 to 93 billion light-years across. Big in age, about 8 billion years since the hot Big Bang. Big in content, hundreds of billions of galaxies or more, with enormous uncertainty in the faintest populations. Big in unknowns, dark matter, dark energy, inflation, the total size, the topology, and the physics of the earliest moments. The universe is big in several different ways at once. If you try to picture the observable universe from outside, you are already picturing something no observer can actually do. There is no confirmed outside space from which to view it. The spherical shape belongs to our horizon, not to a physical ball floating somewhere. A more accurate mental image is being inside the data, with every direction opening into older light, farther galaxies, greater redshift, and finally, the microwave background. The observer is not looking at the universe from beyond. The observer is one event inside the universe, receiving signals from other events. That may be the most important shift. The universe is not an object placed before us. It is the system that contains the observer, the instruments, the light, the galaxies, and the horizon. Measuring its size is therefore unlike measuring anything else. There is no outside ruler. There is no second universe to compare. There is only internal evidence, mathematical structure, and signals limited by causality. Cosmology is the science of learning the container from inside the container. Because we are inside, every answer remains framed by what can reach us. The observable universe is not small, but it is not necessarily representative in every possible way. If inflation created regions with different properties far beyond our horizon, we may never know directly. If the universe is infinite, our patch may be typical or not, depending on assumptions. The cosmological principle is supported within what we see, but beyond the horizon it is an extrapolation. A reasonable extrapolation, perhaps, but still an extrapolation. The strength of modern cosmology is that it does not need to pretend otherwise. It can say what is observed, what is inferred, what is modeled, and what remains unknown. The observable universe has a measured scale. The whole universe does not. The early universe has strong evidence from the CMB and nucleosynthesis. The first instant remains uncertain. Dark matter has strong gravitational evidence. Its particle nature is unknown. Dark energy has strong expansion evidence. Its physical explanation is unknown. The map is impressive partly because its blank regions are honestly labeled. A final scale comparison may help, though only for a moment. Light circles Earth about 7.5 times in 1 second. It reaches the Moon in just over a second. It reaches the Sun from Earth in 8 minutes. It needs years to reach the nearest stars, tens of thousands of years to cross the Milky Way, millions of years to reach nearby galaxies, and billions of years to arrive from the deep universe. During those billions of years, the space it crosses expands. That last clause is what turns 13.8 billion years of age into a 93 billion light-year observable diameter. The oldest light in the sky is not at the edge because it is tired or weak. It is at the edge because it defines the earliest electromagnetic surface we can see. It arrives from all directions with nearly the same temperature, carrying small variations that later became structure. Every telescope pointed at distant galaxies is working inside the universe, shaped by those variations. Every galaxy cluster, every void, every filament, every star-forming region is part of the grown pattern. The observable universe is the matured consequence of a very young glow. If the whole universe extends far beyond that glow, it is hidden not by fog or dust, but by causality. No instrument can defeat the requirement that information must arrive. Science can infer beyond direct observation only when the observable part contains clues. That is why curvature, topology, inflation, and large-scale uniformity matter. They are the clues available. They do not give a final map, but they say the visible region is probably not all that exists. The cosmos we see is a horizon-limited sample of a larger physical reality. The word horizon is useful because it preserves the difference between limit and ending. At sea level, the horizon is not the edge of Earth. It is the farthest distance your line of sight reaches before curvature hides the surface. Move higher, and the horizon changes. The cosmic horizon is not the same kind of geometry, but it shares the lesson. A horizon belongs to the observer, and to the path information can take. It is real, but it is not a wall. Beyond a horizon, the world does not have to stop. Unlike an ocean horizon, we cannot simply climb a mast high enough to see past the cosmic one. We can wait, and more old light can arrive from some regions. But dark energy limits future access. We can improve instruments, and fainter things inside the horizon become visible, but the fundamental boundary remains. We can test models, and perhaps infer more about the unobserved whole, but inference is not sight. The universe gives knowledge in layers, and some layers may be permanently beyond direct reach. The script of cosmic size therefore ends without a final total. That is not an unfinished thought. It is the correct shape of the answer. The observable universe has a diameter. The whole universe has no known measured diameter. It may be infinite, or finite beyond our horizon, or connected in a way that current data cannot reveal. What we can say is already extraordinary. The part from which light has reached Earth spans roughly 93 billion light-years today, and the oldest light we see began its journey when the universe was only about 380,000 years old. When the next deep image appears on a monitor, it may look at first like a scatter of small colored marks. Some marks will be stars in our own galaxy. Some will be nearby galaxies. Some will be distant galaxies reddened by expansion. Some will be noise. A researcher will check the catalogs, inspect the spectra, compare filters, and decide which points are real. The universe enters knowledge through that careful sorting. The biggest thing we can study arrives as faint marks on a detector. Far from that monitor, the galaxies themselves continue. Stars orbit inside them. Gas cools or heats. Black holes feed or wait. Planets turn around their suns. Photons leave in every direction, most of them never crossing Earth. Some begin journeys that will end in future telescopes. Some will never reach us. Some have already arrived after crossing almost all observable time. The cosmos is not waiting to be understood, but it is understandable in pieces, because light and gravity preserve traces. A measured universe also depends on clocks. Cepheid variables brighten and fade with regular periods, and those periods reveal their intrinsic brightness. Supernova light curves rise and decline in recognizable patterns. Pulsars rotate with astonishing stability. The cosmic microwave background records a time when photons decoupled from matter. Each clock works on a different scale, from days to billions of years, and each one helps build the ladder between local measurements and cosmic history. Time is not separate from distance in astronomy. It is one of the ways distance becomes measurable. The calibration of those clocks is not trivial. Cepheids must be measured in nearby galaxies where crowding, dust, and metallicity can affect their apparent brightness. Supernovae must be corrected for color, decline rate, host galaxy properties, and selection effects. Parallax measurements from space missions improve the foundation, but uncertainties propagate upward. Cosmologists argue over small differences because small differences matter when they are multiplied across billions of light years. The universe's size rests not only on grand theory, but on the careful treatment of ordinary-looking stars. Dust is one of the quiet complications. In the Milky Way, in distant galaxies, and in the space between stars, dust grains absorb and redden light. A galaxy can look farther away or older than it is if dust is not accounted for correctly. Infrared observations help because longer wavelengths pass through dust more easily, but dust also glows in infrared when warmed by stars. Astronomers must separate intrinsic color from reddening, young stars from old stars, and distance from obscuration. The darkness between galaxies is simple compared with the dusty interiors of galaxies themselves. Chemical composition adds another clue. Early galaxies tend to have fewer heavy elements because fewer generations of stars have lived and died. Spectral lines reveal oxygen, carbon, nitrogen, iron, and other elements when the data are strong enough. A galaxy's metallicity can show how much star formation has already happened. This helps place the object in cosmic history. In a very large universe, age is not stamped on an object directly. It is inferred from light, redshift, chemical content, stellar populations, dust, and the structure of the galaxy itself. A distant galaxy is often unresolved, meaning the telescope cannot separate its individual stars. The entire system becomes a blended source. Astronomers model its stellar population by comparing colors and spectra to possible combinations of stars. A young galaxy with hot massive stars has a different spectral shape from an older galaxy dominated by red giants. Star formation leaves emission lines in gas. Dust changes the slope of the light. The result is not a direct biography, but a constrained reconstruction. Even inside the observable universe, distance turns detail into inference. Nearby galaxies help interpret distant ones. The Magellanic Clouds, dwarf galaxies around the Milky Way, starburst galaxies, quiet ellipticals, and merging systems provide laboratories for processes that also occurred in the deep past. By studying them in detail, scientists improve models used for galaxies too far away to resolve. The universe's size means we cannot inspect every object closely, so local examples become guides. They are not perfect copies of early galaxies, but they show how gas, stars, dust, gravity, and feedback behave under conditions that can be measured more completely. The local group is also a record of smaller mergers. Stellar streams around the Milky Way show where dwarf galaxies were torn apart. The Gaia mission has measured positions and motions of stars with extraordinary precision, revealing past collisions in the galaxy's history. These local fossils help explain how galaxies grow. When we look at distant galaxies merging billions of years ago, the Milky Way's own halo shows that such events are not remote abstractions. They are part of the history of the place from which we measure the universe. The galactic halo extends far beyond the bright disk. It contains old stars, globular clusters, streams, hot gas, and dark matter. The visible Milky Way is only the bright inner part of a larger gravitational system. This matters for scale because galaxies overlap through halos before their stellar disks collide. Andromeda's halo may already interact with the Milky Way's halo in a loose sense. The luminous parts remain separated by millions of light years, but the faint outskirts of galaxies are larger and more diffuse than photographs suggest. Photographs themselves can be deceptive. A processed image of a galaxy may use colors assigned to filters that human eyes would not see directly. Brightness may be stretched to show faint details. Cosmic rays may be removed. Multiple wavelengths may be combined. These choices are not dishonest. They reveal structure hidden in raw data. But they remind us that images of the universe are translations. The real object is light measured through instruments, not necessarily the color picture that later appears in a documentary or on a screen. The same is true of all sky maps. The cosmic microwave background is often shown as an oval map covered in red and blue patches. The oval is a projection, like a map of Earth. The colors are exaggerated temperature differences. The Milky Way foreground has been modeled and subtracted. Without explanation, the image can look like a surface surrounding the universe. With explanation, it becomes something more precise, the oldest light arriving from all directions, projected onto a map so humans can study its pattern. Projection is another hidden issue in cosmic maps. A three-dimensional distribution of galaxies can be flattened into a two-dimensional figure, and the figure can make filaments look closer or more connected than they are. A slice through a survey shows only part of the volume. A simulation rendering chooses density thresholds and colors. Maps are essential, but they are never the universe itself. They are instruments of understanding. To ask how big the universe is, we have to ask how the map was made. The most familiar map of Earth has edges because paper has edges. A map of the observable universe has edges because observation has a horizon. Neither edge should be mistaken for the end of the underlying world in the same simple way. Earth continues around the globe beyond the map boundary. The universe likely continues beyond our observable boundary, though not in a way we can circumnavigate. The analogy is imperfect, but it helps separate a representation from the thing represented. Because of expansion, there are galaxies whose light we see from when they were young, but whose current recession places them beyond the region we could ever reach. This produces a strange asymmetry. The past is visible, the future is disconnected. A telescope can gather ancient evidence from a galaxy that no future spacecraft or radio signal could ever contact, even in principle under current physics. The universe is not only too large for technology, in some directions and distances, it is too large for causality. This does not make local exploration meaningless. The solar system remains physically reachable compared with the stars, and the nearby stars remain meaningful targets for telescopes and perhaps very long-term probes. Each scale has its own kind of access. We can land on Mars. We can orbit Jupiter. We can image disks around nearby stars. We can measure exoplanet atmospheres. We can map galaxies. We can infer the CMB. The fact that some regions are unreachable does not erase the regions that are open to measurement. The solar system also gives a grounding contrast. A comet from the outer reservoir may spend millions of years falling inward before becoming visible near the Sun. Its orbit records weak gravitational nudges from passing stars, galactic tides, or planetary encounters. A grain of dust in a meteor shower may come from a comet trail. A meteorite in a laboratory may preserve material older than Earth. These small samples do not measure the universe's diameter, but they show that cosmic history can be held in pieces when those pieces come from nearby. Meteorites connect the local to the galactic. Their isotopes reveal conditions in the early solar system and sometimes traces of presolar grains that formed around older stars. Those grains existed before the Sun, before Earth, before any telescope. They were carried into the cloud that formed our system. In a universe too large to traverse, matter itself sometimes carries records across time. The largest scales are measured with light, some local histories are measured with samples. Both forms of evidence belong to the same cosmos. The search for the universe's size also depends on mathematics that cannot be seen directly. The scale factor describes how distances between unbound points grow with time. The metric describes space-time geometry. The density parameters describe contributions from matter, radiation, curvature, and dark energy. These are abstract quantities, but they are tied to observations. When a spectral line shifts, when a supernova appears dim, when the CMB pattern changes with angle, the abstract quantities become constrained. Mathematics is the bridge between faint light and cosmic size. General relativity is the framework under that bridge. It treats gravity not as a force acting through fixed space, but as the curvature of space-time by matter and energy. On solar system scales, it explains Mercury's orbit and light bending near the Sun. On cosmic scales, it allows the universe itself to expand. The same theory that predicts gravitational lensing by galaxy clusters also supports the equations used for the expansion history. The universe is measured through a theory that has been tested in many regimes, though the largest scales continue to test it further. If gravity behaved differently across cosmic distances, the inferred size and composition of the universe could change. Modified gravity theories attempt to explain some observations without dark matter or dark energy, or with altered behavior at large scales. These ideas are studied, tested, and constrained. So far, the standard model with dark matter and dark energy remains the most successful broad description, but the search continues. The scale of the universe is partly a test of whether gravity works the same way everywhere we can observe. One reason dark energy is difficult is that it does not clump like matter in the simplest model. Dark matter gathers in halos. Ordinary matter cools into galaxies. Dark energy appears smooth, associated with space itself, or with a field that changes slowly. Its effects become noticeable over enormous distances and long times. You do not find a dark energy cloud in a telescope image. You infer its presence from the expansion history. That makes it powerful and elusive at the same time. The cosmological constant is the simplest version, a constant energy density of empty space. As the universe expands, matter becomes more dilute, radiation becomes more dilute and redshifted, but the density of a cosmological constant remains the same. Eventually, it dominates. This simple idea fits many observations, but it raises deep questions in fundamental physics. Why this value? Why so small compared with naive quantum expectations? Why important now in cosmic history? The size of the universe leads directly into these unresolved questions. Matter domination allowed structure to grow. Dark energy domination limits future growth across the largest scales. Galaxy clusters that are already bound can continue evolving, but the formation of new large bound structures slows as expansion accelerates. The cosmic web we observe today is therefore not just a present pattern, it is a stage in a changing balance. Earlier, gravity built structure more effectively. Later, expansion isolates it. The observable universe contains evidence of both eras. If the universe were viewed in a simulation with cosmic time accelerated, filaments would sharpen, clusters would merge, voids would expand, and then large-scale growth would slow. Galaxies inside groups would continue interacting. Stars would age, gas supplies would decline. The overall web would not simply freeze, but its ability to draw new distant matter into bound structures would weaken. This future is far beyond human time, yet it follows from the same equations used to calculate the present horizon. The present horizon is also shaped by radiation from the earliest times. The CMB was released at redshift about 1100, but photons from even earlier epochs could not travel freely. Before recombination, the universe was filled with plasma. Photons scattered constantly. The concept of seeing an object before that time with light does not apply in the usual way. It is like trying to see through a fog that is everywhere and is part of the medium itself. The fog cleared when neutral atoms formed. The word surface in surface of last scattering can mislead because it suggests a physical shell. It is better understood as the set of locations and times from which the photons now reaching us last scattered before traveling freely. For us, that set forms a sphere on the sky because we look outward in all directions. For another observer elsewhere, the sphere would be different. The CMB is universal, but each observer's last scattering surface is centered on that observer's world line. Small changes in the CMB temperature correspond to early density differences, but the map also contains polarization information. Polarization shows how light was scattered and can reveal additional details about early conditions. Measuring it is difficult because the signals are faint and foregrounds matter. Scientists search for patterns called E modes and B modes, with primordial B modes being a possible sign of gravitational waves from inflation. The search is careful because a false detection would mislead the whole story of the early universe. The universe is large enough that patience becomes a scientific instrument. Some stars must be monitored for years. Some surveys require decades to build proper motions or time domain catalogs. Some gravitational lenses use time delays between multiple images of a variable source. Some pulsar timing arrays search for low-frequency gravitational waves by watching tiny timing deviations across many pulsars over long spans. The cosmos changes slowly on human scales, so astronomy often advances by extending the human moment through records. Archives make that possible. A photographic plate from a century ago, a radio survey from decades ago, a Hubble image from the 1990s, a Gaia data release, a web spectrum, and a future survey can be compared. Objects move, brighten, dim, explode, or remain steady. The universe is too large to revisit in person, but the sky can be revisited by instruments. Time baselines turn still images into motion and evolution. A larger universe becomes more understandable when records accumulate. There is another meaning of big that belongs to information. The observable universe contains more detail than any catalog can fully store in human-readable form. Every star has a history. Every galaxy has an assembly path. Every dust grain has a chemical origin. Every photon has a trajectory. Science compresses this detail into laws, parameters, and representative models. Compression is necessary. Without it, the universe would be a collection of facts too numerous to use. The measured size is one of the greatest compressions, a single number standing for a horizon of almost unimaginable content. A single number can also hide uncertainty. About 92 billion light-years across is a rounded public value. More technical values depend on parameters from Planck and other datasets, including the Hubble constant, matter density, and curvature assumptions. The difference between 92 and 93, or 94 billion light-years, is not the main issue for a voiceover like this. The main issue is the concept. The present-day observable diameter is much larger than 27.6 billion light-years because expansion changed the distances while light traveled. When people object that nothing can move faster than light, they are defending a real principle but applying it to the wrong quantity. Special relativity limits motion through local space. Cosmological recession is not ordinary motion through a static background. It is the increase of distance due to the expansion of space in general relativity. Locally, light always moves at light speed. Across cosmic distances, the bookkeeping of distance and time is different. The universe does not break relativity. It requires the full version of relativity to describe it. The speed of light still rules the observable universe. It creates the horizon. It delays every message. It turns distance into look-back time. It prevents instant knowledge of the cosmic present. Expansion does not free us from that limit. It makes the limit richer. The horizon exists because light speed is finite, and the universe has a finite age since the hot Big Bang. The event horizon exists because expansion accelerates. Both are consequences of physics, not failures of it. If a civilization existed in a galaxy 10 billion light-years away in look-back time, what we see would be that galaxy's ancient state. Its stars have aged. Some have died. Its structure may have changed. It may have merged. Any life there, if it existed, would belong to a history inaccessible to direct present observation. The scale of the universe prevents easy stories about simultaneous neighbors. Distant galaxies are not faraway countries sharing the same now in a practical sense. They are ancient chapters arriving as light. This is why the universe's size can feel lonely without becoming mystical. The loneliness is not a supernatural darkness. It is the physical separation imposed by distance, time, and expansion. The evidence still reaches us. It reaches us as photons, waves, particles, and gravitational effects. It is enough to build a science, but not enough to remove all separation. The universe is connected by laws and disconnected by horizons. The cosmic web also means our location is not isolated in the present epoch. The Milky Way belongs to flows of galaxies moving under gravity. The local group moves relative to the CMB frame. Nearby galaxies trace attractors and voids. Peculiar velocities reveal mass distributions. Our galaxy is not fixed against a cosmic backdrop. It participates in structure. Even the act of defining rest on cosmic scales uses the microwave background as a reference, because its dipole pattern shows our motion relative to the average cosmic frame. That dipole is much larger than the tiny primordial fluctuations in the CMB. It comes from our motion, not from the early universe's density seeds. Removing it is part of making the primordial map. This is a small example of how local effects must be separated from cosmic ones. The Earth orbits the Sun. The Sun orbits the Milky Way. The Milky Way moves within the local group and relative to the CMB. Every measurement begins in motion. The stillness of a cosmic map is produced by correcting for that motion. Corrections do not make the maps artificial. They make them honest. If you want to know the early universe, you remove the foregrounds and motions that obscure it. If you want to know the Milky Way, you study those foregrounds themselves. The same data can be contamination for one question and signal for another. The universe is layered, and astronomy often works by deciding which layer matters for the question being asked. For the question of size, the relevant layers are distance indicators, redshift, expansion history, horizons, curvature, and the CMB. Planetary nebulae, exoplanets, supernova remnants, and black holes enrich the story because they show what fills the cosmos, but they do not set the horizon. The horizon is set by spacetime. What fills it is set by the evolution of matter and energy inside that spacetime. Both parts are necessary to make the universe feel real rather than abstract. The observable universe is not a hollow sphere with Earth at the middle. It is filled throughout with galaxies at many distances and times. The outermost electromagnetic layer is the CMB, but inside it there are countless shells of later history. A redshift survey is like sampling those shells. Nearby shells show mature galaxies. Distant shells show younger ones. The farther shells become harder to observe, not because they are less real, but because their light is fainter, redder, and older. At the end of the measurement, the human scale returns. A person can stand outside under a dark sky and see only a few thousand stars with the unaided eye under excellent conditions. Most of those stars are nearby in the Milky Way. The observable universe beyond them is invisible without instruments. Yet the same sky contains the directions of every deep field, every quasar, every cluster, every patch of microwave background. The vastness is not absent from the naked eye sky. It is hidden behind the limits of our senses. A telescope does not change the sky, it changes the threshold. More aperture collects more photons. Longer exposure gathers fainter light. Better detectors reduce noise. Space observatories avoid atmospheric absorption. Interferometers sharpen resolution. Spectrographs turn color into physics. Each improvement lowers a barrier between the observer and the already existing universe. The cosmos was always there. The history of astronomy is the history of becoming less blind to it. The same will be true in the future. New instruments may find fainter galaxies, map dark matter better, refine dark energy, detect primordial signals, or reveal unexpected populations of objects. They may change parameter values and improve the distance scale. They may deepen the observable universe's inventory. But unless physics surprises us in a profound way, they will not let us see the entire universe if the entire universe extends beyond our horizon. The distinction between better vision and unlimited vision will remain. So the final answer keeps two truths together. The observable cosmos is physically enormous and scientifically measured. The total cosmos is physically larger and scientifically unmeasured. One truth satisfies the need for a number. The other preserves the boundary of knowledge. Together they are more accurate than either alone. The universe is not made smaller by being measurable in part, and it is not made less real by being unknown in full. Perhaps that is why the question remains powerful. It begins as a request for size and becomes a lesson in observation. To know how big the universe is, you must know what light can do, what expansion does to light, what instruments can measure, what models infer, and where inference stops. The answer is not only a distance, it is a map of the relationship between reality and evidence. The deep field on the monitor is still only a small patch. Some points in it are nearby stars. Some are galaxies whose light crossed most of cosmic history. Some are magnified by gravity. Some are reddened by dust. Some are too faint to classify. Beyond them lies the microwave background, and beyond that, the part light cannot show. The frame is finite. The implication is not. The difference between a boundary of sight and a boundary of existence is the heart of the subject. A boundary of sight depends on signals. A boundary of existence would require knowledge of what space itself does beyond all signals. Cosmology can test the first with light, redshift, background radiation, and structure. It can only constrain the second through geometry and consistency. That is why the measured answer is precise enough to be useful and incomplete enough to remain open. The universe may contain regions whose light will never arrive, but the part that has arrived is already a physical record of extraordinary depth. It contains the afterglow of the hot early plasma, the growth of dark matter structure, the formation of galaxies, the deaths of stars, the rise of heavy elements, and the quiet widening of distances under dark energy. The observable universe is not everything, but it is not a small clue. It is the largest evidence field science has ever had, and every improvement in measurement makes that field a little more detailed, a little more difficult to dismiss. Even that final sentence is only a local statement from one world at one time. Another observer, far beyond our horizon, would draw a different sphere of evidence around their own sky, and the universe would still continue through laws neither observer can fully surround. The last image is not an edge, It is a dark field growing deeper as exposure time accumulates. Points become galaxies. Galaxies become a web. The web fades into the microwave glow. Beyond that glow, the equations continue farther than the light can show. The mirror keeps collecting what can arrive. The detectors keep counting. The map remains open at its boundary, not because nothing is there, but because the universe is larger than the messages that have reached us so far.